Halo, halo. Halo, halo. Halo, halo, cek, 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 cek. Halo.
Good morning, ladies and gentlemen. Welcome to the 8th India Radar Meteorology Conference, iRAD 2026, initiated by the Ministry of Earth Sciences, Government of India, and hosted by Gauhati University. Guwahati University is hosting the School on Radar Meteorology for Complex Terrain today. This is a flagship scientific forum initiated by the Ministry of Earth Sciences, Government of India, to advance research in radar meteorology. Since its inception in 2017, iRAD has evolved into a vibrant platform that convenes leading scientists, technologists, and professionals across the world to share insights, breakthroughs, and emerging trends in radar-based atmospheric observation, extreme weather forecasting, and climatic analysis. Now, to set the ball rolling for the function, I request the esteemed dignitaries to take their seat on the dais. I request Honorable Vice Chancellor, Gauhati University, Professor Noni Gopal Mohanto, to kindly take a seat on the dais. I request the guest of honor, respected Dr. Soma Sen Roy, Head Radar Division, IMD, to kindly take her seat on the dais. I request guest of honor, respected Dr. Sanjay O'Neill Shaw, Head RMC Guwahati, to kindly take his seat on the dais. I also request Professor Utpal Horma, Registrar Gauhati University, and Convener iRAD, Professor Dhrubajyoti Sahoria, to kindly take their seats on the dais. We would now like to felicitate our esteemed guests. I request Gauhati University members to kindly felicitate Guest of honor, Dr. Soma Sen Roy, Head, Radar Division, IMD. I request Sushmita Das to kindly felicitate Dr. Sanjay O'Neill Shaw, Head, RMC Guwahati. We would also like to felicitate our Honorable Vice Chancellor, Gauhati University, Professor Noni Gopal Mohanto. Registrar, Gauhati University, Professor Utpal Horma. And Convener iRAD 2026, Professor Dhrubajyoti Sahoria. It is indeed a matter of pride that today Gauhati University is hosting iRAD 2026. Gauhati University was founded on 26 January 1948 and has emerged as the first university of Northeast India. Accredited with NAC A+ grade, Gauhati University, with its 47 departments and several research centers, has been a beacon of academic and scientific excellence for over 7 decades. Among these, ST Radar Center stands as a testament to the university's commitment to cutting-edge research. I now request Professor Dhrubajyoti Sahoria, Convener iRAD 2026, to kindly deliver the welcome address.
Distinguished dignitaries, respected scientists, honored guests, delegates, young researchers, and dear students. On behalf of Gauhati University and the organizing committee, it is my great privilege to welcome you all to the inaugural session of 8th Radar Meteorology Conference being held from 6 to 9 January 2025 at Gauhati University, Assam. We are particularly delighted to begin this conference with a radar school on today, specially designed for budding researchers and students. This initiative reflects our collective commitment to capacity building, skill enhancement, and nurturing the next generation of atmospheric scientists by providing direct interaction with leading experts in the field of radar meteorology. We are deeply honored to have Dr. M. Ravichandran, Secretary, Ministry of Arts Sciences, Government of India, to deliver the inaugural address online. His leadership and vision have significantly strengthened India's art system science ecosystem, and his presence adds immense value to this occasion. We are equally privileged to have Dr. Soma Sen Roy, Head, Radar Division, India Meteorological Department, with us as a guest of honor. Her pioneering contributions to the radar meteorology and extreme weather studies continue to inspire researchers and practitioners alike. I extend a warm welcome to our university leadership, Professor Nonigopal Mohanto, Honorable Vice Chancellor of Guwahati University, and Professor Utpal Harma, Registrar Guwahati University, whose vision and support have enabled Guwahati University to contribute meaningfully to the national scientific missions. Guwahati University, established in 1948, is the oldest university in entire Northeast India, and GU is making constant effort to make meaningful contribution to the research and innovation ecosystem of the country. We believe that organization of 8 radar school will immensely benefit our researchers of the region and inspire them by presence of experts in the field. We are honored by the presence of eminent scientists, including Professor V. Chandrasekhar from Colorado State University, Dr. Nobuhiro Takahashi, Nagoya University, and Professor B.N. Goswami, PM Professor at Gauhati University, whose seminal contribution continue to guide monsoon and climate research in India. This conference holds special relevance to Northeast India, a region highly vulnerable to extreme rainfall, floods, landslide, thunderstorms, and climate variability. Strengthening radar-based observations and research here directly supports the MOES IMD mandates, the Sendai Framework for Disaster Risk Reduction, and India's vision for Viksit Bharat 2047. For young researchers of this region, the radar school and technical sessions offer a unique opportunity to engage with cutting-edge tools, national observing systems, and collaborative research pathways. With delegates and participants from across the country, this platform fosters knowledge exchange, innovation, and partnerships that will advance operational meteorology, climate services, and societal applications. The organization of this seminar is made possible by the support of our sponsors. Their helping hand for the cause of progress of science is remarkable. We are thankful to them. Once again, I extend a warm welcome to all of you and wish the 8th Radar Meteorology Conference and Radar School a great success. Thank you very much.
Thank you so much, sir. It is a matter of great pride that we have with us today Dr. M. Ravichandran, Secretary, Ministry of Earth Sciences, who have joined us online. Welcome, sir. Professor Nonigopal Mohanto is a respected academician and administrative leader who has strengthened Guwahati University's role as a center of higher learning, research, and innovation for the Northeast India. I request Honorable Vice Chancellor Professor Mohanto to kindly address the gathering.
Namaskar and good morning to all of you. Honorable Secretary MOES Dr. M. Ravichandran Dangoria, Honorable guest present today Dr. Soma Sen Roy, Head Radar Division IMD, Dr. Sanjay O'Neill and other distinguished scientists, dear participants, and my faculty members and esteemed registrar and other office bearers of Guwahati University. First of all, I do have the honor and privilege to welcome all of you to this iRAD 2026 Radar School Conference being organized by Guwahati University. I extend my warm welcome to the Honorable Secretary, Ministry of Arts Sciences, the other senior scientists from India Meteorological Department, distinguished experts, delegates, and young researchers from India and abroad. It's a matter of great pride for Guwahati University to host the Radar School under the umbrella of iRAD 2026. Northeast India, as you know, is a melange of various ethnic and linguistic groups, and it is also a truly natural laboratory for atmospheric research. The region experiences frequent high-intensity rainfall, prolonged wet spells, and increasingly severe heat extremes. These extreme meteorological events and phenomena often result in loss of human life, public property, and livelihood. Well, extreme rainfalls events lead to recurrent flood and severe erosion in the Brahmaputra basin. This is not necessarily a scientific phenomenon, but also having its manifestation in the social and political dimension, because it leads to displacement. Displacement leads to identity crisis in many areas, as we see its manifestation in Assam and in other parts of Northeast India today. The process significantly impacts the regional ecosystem, agriculture, infrastructure, and socio-economic stability. Despite this vulnerability, systematic and sustained scientific research in the region is still limited. Guwahati University is deeply committed to climate and atmospheric research, particularly focused on the northeastern region. We have also forged an MOU and understanding with TERI for initiating a Himalayan studies on climate research. Capacity building, advanced training, and regional leadership in weather and climate science are among our top core priorities. In this direction, we have already taken a major step by associating Professor B.N. Goswami as Professor of Excellence at Guwahati University, and I congratulate Sir for having been recognized as recently Prime Minister Professorship. We are also planning to establish a dedicated center for climate and cloud research, which will act as a hub for advanced research, training, and national and international collaboration. I am proud to inform you that Guwahati University hosts a state-of-the-art stratosphere and troposphere radar system. This sophisticated facility provides a rare opportunity to study atmospheric dynamics of the region, including various precipitation processes and extreme weather systems. With proper support, this radar can play a transformative role in regional weather and climate research. To move forward more meaningfully, we solicit and request continued support from the Government of India, especially Ministry of Arts Sciences. Support is needed not only for sustained research activities, but also for the operation, maintenance, and upgradation of the present SD radar system that we have at Guwahati University. Well, conclusively, I take this opportunity to appeal to the Honorable Secretary MOES to kindly support our system, that is ST radar system at Guwahati University, in strengthening climate and radar meteorology research in the region. Platforms like iRAD 2026 are vital for collaboration among meteorologists and atmospheric scientists across different parts of India and the world. I am delighted to see such an enthusiasm among the experts and the participants who have gathered today. I am confident the discussion and the training during Radar School will be scientifically enriching and socially impactful. I compliment my best wishes and wish Radar School and iRAD 2026 every success. With this few words, I welcome all of you, and please excuse us for any kind of omission and commission if you happen to come across. With these words, I declare this program being inaugurated. Thank you.
Thank you so much, sir, for your thought-provoking words. I now request Registrar, Gauhati University, Professor Utpal Sharma, to kindly address the gathering.
Good morning. Honorable Secretary, Ministry of Arts Science, Dr. M. Rabichandran Dangoria, Honorable Vice Chancellor, Gauhati University, Professor Noni Gopal Mohanta sir, Professor B.N. Goswami, ANRF Prime Minister, Professor, Guwahati University, Professor Sandra, the head of the RMC, Dr. Sanjay Saw, Dr. Soma Sen Roy, my esteemed colleagues, participants from across the country and abroad, and the students delegates. It is a pride moment for us to host this 8th Radar conference. We had a radar system, ST radar system, a long back. It was installed, it was operational, and data are being generated, but it is not known to the community. And for that reason, we thought that we should conduct this kind of workshop to disseminate what we are going to do and what are the facilities available. With the kind support from Professor B.N. Goswami sir, Professor Sandra sitting behind, and the support from the Indian Institute of Tropical Meteorology, we started this initiative to host this program. I, on behalf of Guwahati University, like to express that we are committed for making a climate research center in Guwahati University. For that, we need support from your expertise. We need support in terms of infrastructure, as Honorable Vice Chancellor Sir has stated clearly. We need support from Government of India, like computational support, training programs that we can conduct here to create manpower in this direction, because we are lacking in manpower in this direction. That is, radar meteorology will be the next level of meteorology for weather forecasting as well as climate research. Guwahati University, being the pioneer, the first university in the northeastern region, we have 47 departments, from mathematics to statistics, information technology to instrumentation, and all these subjects, all these programs can contribute to the climate research, and in fact they are doing work in this direction, from artificial intelligence to instrumentation development for climatic condition study, for model creation. So I think this expertise available in Guwahati University will be, take a big role in doing such kind of research in this direction. IITM Pune, we have collaboration with IITM Pune, and they have installed multiple equipments in our campus, and we are doing collaborative research with IITM Pune. So in that direction, the other organization can also join hands with us to make a vibrant climate research ecosystem in Guwahati University. I welcome you all again to Guwahati University. We have a 531 acres of land with 30% water body and 30% undulated hilly areas. You enjoy your time in the campus, not only in the confined to this hall, PD hall, for your presentation and other thing. In between, you roam around the campus. It's a big campus. It's a green campus. You will enjoy the oldest university of northeastern region. The facilities that we are going to provide you may not be sufficient for you. There are definitely some shortfalls. We request for your kind cooperation in this direction. Those facilities we cannot create it for you for your convenience. With these words, I conclude. Thank you once again.
Thank you, sir, for your inspiring words. We have with us online Secretary, Ministry of Earth Sciences, Government of India, Dr. M. Ravichandran. Dr. M. Ravichandran has been serving as the Secretary to Government of India in the Ministry of Earth Sciences since October 2021. His areas of interest are diverse and include atmospheric physics, ocean dynamics, ocean observing systems, polar sciences, etc. I request sir to kindly deliver the inaugural speech. Sir, would you unmute yourself, please? Sir, you're audible. Yes, sir. Yes, sir.
Very good morning to all of you. Respected Vice Chancellor of Guwahati University, Professor Guwahati, Register Dr. Upal Sharma, and my colleagues, Dr. Sumasen Rai and Dr. Sanjay. And also, I am able to see that some of what is called lead talk provider, actually especially for post-mental, Professor B. N. Goswami and Professor Chandra, and also the trainer, Dr. Takaskahi, and other distinguished invitees, students, friends, and colleagues. Very good morning to all of you, and I wish you all a very happy and healthy and successful New Year 2026. I am extremely sorry that I couldn't be there with you all today due to some other pressing commitments here. Though I want to be there physically with you all, I have planned very well. I want to be there, but unfortunately last minute some other important meeting has been arranged here, so I couldn't avoid. I think this is the 8th radar program. Of course, the importance of radars everybody knows, and especially when the weather changes rapidly in the coming years and frequent what is called extreme events and other things are happening, the importance of radar is more and more needed for our country. Having said that, now we have already more than 45 radars has been installed, and also we plan to install more than another 70 radars in the coming years with the various kinds of X, C, and S-band radars we are planning to install apart from bin profilers and radiometers. I think it is a significant investment under the mission MOSUM, but at the same time we don't have a capacity to maintain this radar, to utilize the radar and operationalize, and many other science to do with this radar. We don't have many capacity in country. I think it is imperative we need to impart such training and knowledge from various sources, whatever is available. We need to definitely augment this capacity in our country. In that endeavor, I think this iRAD is very important and it is in need of the hour. I think it is the 8th conference. I think still we need to, lot of people have to be trained, and especially we need to think about how do we do this data acquisition of the radar in terms of reflectivity or maybe whatever the radial velocity, and also various components we need to understand from the radar acquisition. And also I think university type of this Gauhati University and other thing, they have to be more and more active or maybe involved in signal processing and quality control of the radar, especially how to avoid this ground clutter and anomalous propagation of various things, and also various generation of products. How do we produce the rainfall rate, and how do we generate the winds, and also how do we do various products from the radar. Especially I am very much worried. At the same time we are capable that we have so many radars of different kinds, different manufacturer, all are made in India. But the main problem is how to integrate them. We need to have a merged product. How do we do that merged product? It is really worrisome. I think we need to, somebody has to take up this particular job so that we can take a merged product so that it can be used for the day-to-day nowcasting and various other things. Ultimately, I think maybe those who are sitting in the audience or the university, they have to come out with some proposal. How do we merge product from satellite, radar, or upper air observation, or automatic weather stations, or from modeling? All these things, how do we do some merged product so that we can utilize for the best nowcasting purpose? Also, it is imperative that we need to do some of this radar data how to assimilate into the model, especially reflectivity or radial winds or all these things. How do we assimilate for the better improvement of the forecast need to be done? I think that is also important. And this analysis and nowcasting, and also we need to have various products from this, as I mentioned, that we need to develop. I think more and more research is important, and I am sure that this workshop will provide some clues and directions, but ultimately we need to collaborate with the institutions from various institutions in the country as well as university, and if it is required, industrial partners. I think all the three has to work together for the providing the better services. Yes, I am sure that in the Northeast, the weather patterns are changing rapidly, and I think it is imperative that we need to augment more and more observing system in that region. I am sure in the mission Mausam, we will be deploying more and more instrumentation in the Northeast, and also as Vice Chancellor and Register mentioned, we will definitely look into ST radar, and we will, if it is not working, we will revive, and we will make important contributions so that we can collectively work together. I am very happy to see that Professor B.N. Goswami is there. Definitely it will be very useful for not only the university and the country. His service, his knowledge is very, very need of the hour in not only for radar meteorology but also science of weather and climate. I think with this, I once again thank you all, the organizers, for keeping this capacity building initiatives. I am sure that end of this what is called conference, you will come out with some actionable recommendations so that we will be able to implement for the benefit of society. With this, thank you one and all, and I'm once again apologies for not being there. Thank you.
Thank you so much, sir, for your valuable insights. It gives me immense pleasure that we have with us today Dr. Soma Sen Roy, a renowned scientist, head Radar Division, Indian Meteorological Department, New Delhi. She joined IMD in 1998 as a meteorologist after PG studies in physics from University of Delhi. She has a PhD degree from Vidyasagar University, Midnapur, and her primary fields of interest are analysis and forecast of local severe storms. She is a member of the task team for the document WMO Guide for National Meteorological and Hydrological Services. I request ma'am to kindly deliver her speech.
Namaskar, and thank you for inviting me to the iRAD. Respected Vice Chancellor Sir, Professor Nani Gopal Mohanta, respected Professor Utpal Sharma, Professor Dhubojyoti Saharia, Dr. Sanjay Neil Shaw, our respected Secretary, Ministry of Earth Sciences, Professor Ravichandran Sir, Dr. B.N. Goswami. I see a lot of many seniors, Professor T.N. Rao, Professor Chandrasekhar. I'm honored to be in this particular gathering. My personal interest has been local severe storms, as just said, and I myself, in my 27 years of service, radars has been, I have seen the evolution of Doppler weather radars from the first radar that came to Chennai in 2001 to now, when we have a network of around 47 Doppler radars throughout the country, and we are going more and more with dual polarimetric technology. And the proposal is, as our Secretary just said, under Mission Mausam, we plan to have 126 radars. And not just Doppler weather radars by IMD, the Air Force is also bringing up a lot of weather radars, Doppler weather radars. Our IMD people are members of their RFP team, so there is pretty much complementarity in terms of locating these radars as well as operations. Simultaneously, IITM is also doing a lot, is increasing its network, the urban network. They have already implemented for, Dr. Subrata Das is here, already for Mumbai. Now they're planning to do it for Chennai, for Delhi and I think Chennai. So a lot of development is happening in this field. So earlier, buying one radar used to be a major issue. Now we are going through multiple organizations. The government of India is focusing very primarily on this technology for severe weather, prediction of severe weather events, especially the short-range prediction of weather events. I am an operational meteorologist, and I can definitely say you cannot imagine the value addition that happens to the forecast that we give, suppose in the morning. This changeover that has happened from maybe one daily forecast to 3-hourly nowcasting, it does save lives. At the end of the day, all this gathering, this radar, everything is being funded by taxpayer money. We have to remember that we are answerable at the end of the day with all this technology that the people are giving us through the government of India. This has to have an accountability, and this is my target, that my personal target, and also our Ministry of Earth Sciences target, that this should be, these facilities should ultimately benefit the people. We have many leading lights in radar meteorology here, and this kind of a gathering, I think Professor Chandrasekhar first started it, so this is the 8th time, I think. So it's a very necessary gathering, and I wish you all the best, and I hope to see many of you in IMD as our as employees in the radar division, and also to work in radar meteorology throughout the world. Thank you.
Thank you so much, ma'am, for your inspiring words. I now request today's guest of honor, Dr. Sanjay O'Neill Shaw, Head RMC Guwahati, to kindly address the gathering.
Namaskar. Respected Professor Nani Gopal Mahanta, Honorable Vice Chancellor, Guwahati University, Professor Utpal Sharma, Registrar, Guwahati University, Professor Dhruv Jyoti Saharia, Convener of iRAD 2026, Dr. Soma Sen Roy, Head of Radar Division, IMD, Professor B.N. Goswami sir, and Dr. M. Ravichandran sir, Secretary MOES, and also Professor P. Chandrasekhar, and all the dignitaries, researchers, and students. It is my great pleasure to speak on the occasion of the 8th edition of iRAD, that is India Radar Meteorology Conference. Since its inception in 2017 at IIT Kharagpur, iRAD has steadily grown into a vibrant and respected platform dedicated to advancing the science and applications of radar meteorology in our country and beyond. Over the past decade, radar meteorology has evolved from a specialized area of research into a key foundation of modern weather forecasting and climate services. Today, Doppler weather radars are at the heart of real-time monitoring of severe thunderstorm, heavy rainfall, cyclones, hails, and other high-impact weather events. iRAD plays an important role in bringing experts, professionals, and students together. Now, radar data is combined with weather models, satellite information, and forecasting techniques which help in improving disaster management. In Northeast India, there are presently there are three Doppler weather radars, one in Mohanbadi, one in Agartala, and another one is in Cherrapunji. So, and IMD is installing a dense network of radars in northeastern region. And for your kind information, the installation of Doppler weather radar at Guwahati is already complete, and soon we are going to commission it, and it will be helpful for our public. And moreover, other Doppler weather radars are coming up in Tezpur, Silchar, Kohima, Imphal, Aizwal, Belonia, and also some more in some more places, because we are hunting for getting the right location for the setting up of the radars. So in the 2026 edition of this conference carries a special significance, because for the first time iRAD has been hosted in northeastern region of India, that is here in Guwahati University. The Northeast is one of the most meteorologically dynamic and sensitive regions in our country, with complex terrain, intense convection, heavy monsoon rainfall, frequent thunderstorms, and unique hydrometeorological challenges. Hosting iRAD here provides a valuable opportunity to apply advanced radar science to address the specific weather and climate challenges of this region. Equally, important role of iRAD is building sustained collaborations. Today, radar meteorology and the technology is not driven by science alone, but it is strengthened by close partnerships across government agencies, private industry, startups, and academia. iRAD 2026 aims to foster business to business, business to government, academia, industry linkages, and these partnerships are essential for design modifications, improving data network, developing decision support tools for disaster management, and delivering high valued services like aviation, agriculture, renewable energy, urban planning, etc. As India rapidly expands its radar network and modernizes its weather and climate services, conferences like iRAD provide the intellectual and collaborative foundation we need. They inspire us to share ideas, learn together, and turn scientific discoveries into practical solutions that save lives and properties and help community face climate challenges. I extend my warmest wishes for the success of iRAD 2026 at Guwahati University. May this conference inspire new ideas, new partnerships, and new commitments to harness radar meteorology for a safe, more informed, and more climate resilient India, especially for the region like Northeast India, where every improved forecast can make a profound difference. Thank you, and Jai Hind.
Thank you so much, sir. I now request Dr. Homiron Padgiri, Joint Convener iRAD 2026, to kindly deliver the vote of thanks.
Honorable Vice Chancellor, sir, Honorable Secretary MOES, respected Registrar, sir, respected dignitaries on and off the dais, distinguished guests, esteemed colleagues, and my dear participant. It is my proud privilege to propose the vote of thanks at the conclusion ceremony of the inaugural function of Radar School, which is held in connection of iRAD 2026. At the very outset, on behalf of the organizing committee of iRAD 2026 and Gauhati University, I expressed our deep sense of gratitude to Honorable Secretary, Ministry of Art Science, Dr. M. Ravichandran, for his kind gracing that inaugural session and for his inspiring inaugural address. His vision and continued support to the radar meteorology and atmospheric sciences are a great source of motivation for the entire scientific community. I convey our sincere thanks to Honorable Vice Chancellor, sir, of Guwahati University, for his encouraging address and for his constant guidance and unwavering support in making iRAD 2026 a reality. We are deeply honored by the gracious presence of our guest of honor, Dr. Soma Sen Roy, Head Radar Division IMD, and Dr. Sanjay O'Neill Shaw, Head RMC Guwahati. We are thankful to them for taking the time out of their busy schedule to be with us and sharing their insightful perspectives. I would Also like to place on record our sincere appreciation to our esteemed invited speakers, Professor B.N. Goswami sir and Professor Chandrasekhar sir, for graciously accepting our invitation to deliver the lecture on Radar School. I also extend my heartfelt thanks to Registrar Guwahati University Professor Utpal Sharma sir for his continuous supporting in turning this event into a reality at Guwahati University. Right from the beginning, when I have first proposed of hosting iRAD at Guwahati University during this previous edition in Mumbai in 2025, he has been the driving force behind the planning, coordination, and seamless execution of iRAD 2026 at Guwahati University. My special thanks goes to member of that organizing committee, steering committee, and to all other research scholars and student volunteers for their tireless effort and overhearted cooperation in organization of this event. I also greatly acknowledged the support extended by the Ministry of Art Sciences and other various collaborating institutions for sponsoring in this event. I would like to give special thanks to Samir Mumbai for supporting this radar school. Last but not the least, I thank all the participants present here to making this radar school into a successful event. With this word, I once again thank everyone for their presence and support, and I wish all of you a scientifically enriching and scientific conference. Thank you.
Thank you, sir. I request esteemed dignitaries on the dais to kindly join us on the other side. I now request Dr. Sushmita Das to kindly introduce today's speaker, Professor B.N. Goswami, and to carry forward the next sessions.
हेलो 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 सर কৰিব লাগে নেকি হেল্ল' তেতিয়া মই সেইটো মাইকত হেৰি নকৰিলে হ'ব নহয় ঠিক আছে অন কৰি থাকিব দিয়া চাউণ্ডটো এডজাষ্ট কৰি দিবা
এইটো পঢ়ি লোৱাৰ পিছত ৰেডি কৰি দিব নেকি এইখিনি আচ্ছা মানে প্ৰেজেণ্টেশ্যনটো ওলাই দিব
A warm good morning to one and all present here. It gives me immense pleasure to invite our first esteemed speaker for today's session, Professor Bhupendranath Goswami, who is one of India's most distinguished meteorologists, widely recognized for his transformative contributions to tropical meteorology, monsoon dynamics, and climate modeling. He began his academic journey with a BSc Honours in Physics from Cotton College in 1969, followed by an MSc in Physics from Guwahati University in 1971. He pursued a PhD in Plasma Physics at Gujarat University, conducting research at the Physical Research Laboratory, Ahmedabad, and completed his doctorate in 1976. His postdoctoral years took him to the MIT and NASA's Goddard Space Flight Center, where he worked closely with legendary scientists such as Professor Jules Charny, experiences that deeply shaped his scientific approach. Upon returning to India, he played key academic and research roles at IIT Delhi and the Indian Institute of Science, where he helped advance the study of atmospheric and oceanic sciences. In 2006, he was appointed Director of the Indian Institute of Tropical Meteorology, Pune, leading the institute until 2014. He has also served as a visiting professor at the University of Maryland and Princeton University. Throughout his exceptional career, spanning more than 5 decades, Professor Goswami has received numerous prestigious honors, including the Shanti Swarup Bhatnagar Award in 1995, the Vikram Sarabhai Award, the K.R. Ramanathan Medal, the Kamal Kumari National Award, the National Award in Atmospheric Science and Technology, and the Lifetime Achievement Award in Science and Technology from the Government of Assam. He is a fellow of India's top scientific academies, the Indian National Science Academy, Indian Academy of Sciences, National Academy of Sciences, India, as well as the World Academy of Sciences. His leadership has extended to major national and international scientific committees under WCRP, DST, MOES, ISO, and APN, where he has significantly influenced climate research, policy, and capacity building initiatives. At present, he serves as a SERB Distinguished Fellow at Cotton University and a Professor of Excellence at Gauhati University, where he continues to guide young researchers and contribute to cutting-edge work in monsoon predictability, tropical dynamics, and climate variability. His enduring mentorship continues to shape the scientific landscape and of atmospheric and climate sciences in India and beyond. I would request Dr. Bandana Chaudhary to felicitate Professor Goswami with a Fulam Gamusa.
Thank you so much.
We look forward to your session, sir. Over to you.
Thank you. Thank you very much for that kind introduction. And I think it took too much of our time. I think already we are late. Good morning to all of you, and thank you for coming to this workshop. And I thank you, Professor Sandra, to coming to this Northeast for the first time, I think. And we are hoping to have a very stimulating and fruitful workshop, conference in the next 3 days. So today, I am not a radar scientist, obviously, and I am actually a large-scale atmospheric scientist. But I think the theme of this conference has been because we are in a very interesting complex terrain which shapes the weather and climate of this region, and this is actually a very, very interesting part in the whole world. I think it is one of the very interesting part where the interaction of convection with orography and dynamics play a very important role in shaping the large-scale weather. So what I am going to tell you, not much about radar meteorology, but about how the orography affects the convection in this region, starting from small scale to actually very large scale. And I'll mostly confine to talking about how the orography affects the convection and rainfall and organizes the convection and rainfall in these scales, from mesoscale to synoptic scale to very planetary scales like in the monsoon intraseasonal oscillations. Can you hear me at the back? Okay. So monsoon intraseasonal oscillations and like ITCZ. So in fact it has so much contribution to the control in the Indian monsoon itself is very I think we are beginning to realize only now. Because it is a small place, world meteorologists and even Indian meteorologists have not looked into the physics and dynamics of this interaction in this Northeast region, and has been neglected. In fact, I did not do too much work on Northeast until I came here and settled in 2017, because I was more interested in large-scale monsoon. But within the large-scale monsoon, the Northeast monsoon contributes about 15% or 13% of rainfall. And that is not a small amount. And if the Northeast mountains were not there, not only 13% rainfall would be less for monsoon, it will actually reduce much more, because lot of moisture flux will go to the east and then have much less precipitation compared to this. So it has a very big impact, and we did not realize how important. And I'll tell you a few examples. In the last 6-7 years, we have been doing some interesting studies in the Northeast in terms of the large-scale monsoon and how the local orography affects this large-scale monsoon. So I'll give a series of examples. So this is not going to be a very detailed description of any of the work, but give you a flavor of how, and then in that couple of places I will show where in more detail, little bit of detail, how the small scale orography, see this orography is very special. The monsoon in this region, so the monsoon is essentially, is a part of, Indian monsoon is a part of global monsoon, which is determined by the ITCZ, and this northward migration of this ITCZ during the summer produces the summer monsoon, and that has this kind of a sort of the ITCZ is in the winter somewhere here, and then at the onset time it progresses northward suddenly in a very short time, within a week or so. It propagates fast and then gets established in the north. But at the same time, there is another ITCZ remains here, and the kinetic energy of the atmosphere in the lower atmosphere increases by an order of magnitude at that time. That is how we have this onset takes place. So then the monsoon sets up, but then there is one band of rainfall still remains there. Then by this September, it withdraws. So there is a cycle, there is a seasonal cycle, and the seasonal cycle is associated with the seasonal evolution of the ITCZ. So, so this monsoon is essentially is determined by a very peculiar geographic conditions in this region. So we have these large tall mountains to the north, and the oceans to the three sides of the continent. There is ocean, but the ocean is very warm throughout the year, except during summer in this region, most of the year. So we are sitting, a land is sitting surrounded by a very warm ocean, which produces a lot of moisture, and then the land being heated up, it produces low pressure area. So a lot of moisture converges into land, and there is this big mountain. And therefore, it will produce a lot of rain. So that is how Indian monsoon is this most intense monsoon in the world. So this geography is very important. Within this geography, this northeast is very peculiar. You see, we have tall mountains to the north, and we have a range of mountains which is almost parallel to that. And there is a valley, Brahmaputra Valley. It's a small valley, only about 100 kilometers. To the north, there are 7 kilometer tall mountains. To the south, there is a range of mountains which is 1.5 to 2 kilometers with breaks and so on. But there is a range parallel to that. Between that, there is a valley. Now, summer, the monsoon winds go like that, and therefore these winds can bring moisture and get lifted by the orography and can produce a large-scale orographic rain. You don't need a low-pressure area. So orographic rain can produce organized convection. Orographic rain, normally you will think that it will be bits and pieces, but it is not. In northeast, it produces large-scale organized rainfall. So, so this is very interesting, because this mountain, we must remember that this is where it is makes it very interesting. So this mountain range is like 6-7 kilometers tall, and this mountain range is about, and this is the valley. That is very narrow. Now I'll show you how rain belt. There is one rain belt to the south of this another rain belt here. Within so this orography we call, in meteorology we call them mesoscale orography. So this mesoscale orography actually influences two bands of rain here, another band here, another band here. So between them there is small valley, so it produces a very large scale heat source. And that large scale heat source then can affect the large scale circulation. And that is the important part of this region. So with this, I will tell you, to understand this, I'll give a little, very short, brief introduction to the monsoon, and then about northwest Indian weather and climate variability a little bit, and then finally I'll talk about a sort of, give a little couple of results that we have done in the last few years on how climate change actually affects this. And while doing that, we have discovered that Northeast is very differently affected by climate change than in the central India and the rest of the India, because where the monsoon rainfall is increasing, and in the Northeast it is decreasing, although it is a part of the same large-scale system. And so, and that part of that is not driven by orography alone, but from large-scale global circulation makes that happen, and the orography helps it. And then I'll talk about how the orography affects the onset. organization of rainfall during monsoon onset and sets the onset to happen in May rather than in June. And then finally I'll talk about one of the studies that we did some time back, and now we are doing more of the studies, and so that here the extreme events are controlled very much by the orography. And the orography interaction between the winds and the orography produces certain high-frequency oscillations like the inertial gravity waves. And these inertial gravity waves within a mesospatial system can produce an extreme event. And that is how most of the extreme events become very strong here. Although already we have large moisture content, and the orographic lifting is available, and on the top of that you have a inertial gravity wave, which makes it even more larger vertical velocity and stronger. So just to give you a brief background of what is a monsoon, monsoon is essentially what I call monsoon is a convectively coupled off equatorial heat source in summer. So this rainfall in this region summer, so there is a lot of rain. In winter there is no rain. There is a seasonality of rainfall. That seasonality of rainfall is coupled with a seasonality change of winds. Originally monsoon was defined by winds, seasonality of the winds, but seasonality of winds alone cannot explain the real monsoon. Monsoon circulation itself is very deep, and that monsoon deep circulation is actually produced by the heating associated with this rainfall. Heating produces, the rainfall produces heating in the middle atmosphere, and middle atmospheric heating produces low level convergence and upper level divergence and produces deep circulation. And that is how monsoon is driven by winds, monsoon driven by rainfall. But without winds, rainfall cannot happen. The winds produces the convergence. Initially, the winds generate the convergence, start the convection, and the convection then generates a deep heat source. Deep heat source then produces stronger convection, and then it sustains. So that is why it is a convectively coupled system. The wind and rain cannot be separated. They are together. So that is why many of these old definitions on winds and the paleoclimatic records becomes very difficult to interpret because they seem to be inconsistent. Strong rainfall. Sometimes the strong monsoon, where monsoon rainfall is increasing, then we expect that the wind should be increasing. But sometimes because the convection itself stabilizes the atmosphere, then winds can actually decrease. So you can misinterpret so you have to understand this convective coupling, and that actually only after 80s we have understood this phenomena more clearly, and now we are trying to reinterpret how monsoon should be looked at. So that is why. So we have a low level wind, and then because of that heat, the winds converge into then produce a cyclonic vorticity at the low level, and the upper level this produces a divergence and produces anticyclonic vorticity, and this anticyclonic vorticity due to the angular momentum conservation produces a strong easterly jet. This easterly jet is the only strong easterly jet you can see in the world because of the monsoon. There is no other easterly jet that can be seen. And that, if you plot a vertical circulation, if I take a cross-section in the longitude and plot a vertical circulation, that circulation is actually very deep. It has large ascending motion in the central India and a descending motion south of equator. So this is called a monsoon overturning circulation. And this is very important, which means that any theory must explain that the circulation is deep. If it was only surface heating, just as we thought before, then the circulation will be very shallow. It will be in the boundary layer only. It will not go to the top of the atmosphere. So this is important. So this is the actually the our doesn't run. Okay. So this is the annual cycle of the northward propagation of the rain band. So rain band is the ITCZ, and so it's how in this winter it is here, and then this is what we have plotted here is called and the convective coupling is shown here. So wherever there is large rainfall, their winds are converging there. You see, that is what I call convective coupling. And then and this is the climatological daily rainfall and the winds at 850 millibar, and for the whole I think this bar is not there. Okay, forget it. And then it will go. It will run and go, and then so now it is sort of coming in March, May, and June. Now a monsoon is set up. The more rainfall here and here, and so and the overland also now getting more rainfall organized. So monsoon has set up now, and now and then it will then slowly it will retrace after September. So let me go skip this. And so if I plot that, so interesting thing is that if I plot that rain band as a daily cycle of this rain band around from 70 to 90 degrees, if I plot as a function of latitude and time, this climatological annual cycle, it shows that band I have shown you in the first slide, that the rain band is in the south of equator in the winter, then it goes to the summer and establishes around 25 degrees, 23 degrees, and then there is another one here, then it comes down and goes like that. So this is the annual cycle of our northward migration of the rain band. Now then that is associated with this change in the heat source in the atmosphere. Now heat source is here plotted as a surrogate from the temperature. So atmosphere is heated up, so a temperature anomaly, the middle atmosphere becomes warmer. So if I take the middle tropospheric temperature between 700 and 200, and again between as over a larger area in the north, and then plot it as a function of latitude and time, what we see is that, so this is the warmer region. In the winter, there is a heat source, or the middle atmosphere is warmer to the south and cooler to the north. And then around the onset time, the middle atmosphere becomes much warmer, and then suddenly becomes very warm, and remains there like that during monsoon time. It is warmest, and then again it decreases like that. So this middle atmospheric temperature also has this annual cycle which is very similar to how the rainfall changes, and therefore this is affected by rainfall. So therefore we believe that the onset of the monsoon is related to these changes in the middle atmospheric heating from the south to the north. At the time when it changes the sign, changes the heating, and that is when the onset takes place. That is how we defined a new definition of onset based on this tropospheric temperature. Sometime back, and we have done a lot of work on that, but I will not go into great details. But that is so it can. Therefore, tropospheric temperature can be used because it is a large scale variable, and that change of sign can be used as the onset definition. But that is I'm not going to go into great details of that. But before going to further, I must just mention that the monsoon has very large year-to-year variations. This is a time series everyone knows. The interannual variation of the monsoon. Here what we have done is we have combined this data from the Professor T data as well as Shontake et al. Data, which is based on a smaller number of stations, and extended it for almost 200 years. And so this year-to-year variation of the monsoon produces what we call these years are normalized to its own standard deviation, and therefore above 1 are all these what you call flood years, and these are the drought years. And so there is considerable amount of variation. So an important thing is that there is also some sort of a multi-decadal variability in the monsoon. And so monsoon has quite a bit of interannual and multi-decadal variability. So just keep that in mind, because some of the things, and the multi-decadal internal variability, we have a lot of studies have shown that El Nino and sudden oscillation is a major driver of the interannual variability. But recently we have found that a part of interannual variability is also related to North Atlantic temperatures. And so we have written several papers on that. And including one of the very recent papers where it has shown that so, and this ENSO-monsoon relationship is so the ENSO is a driver, and ENSO is known to be negatively associated with monsoon when the El Nino is strong and the monsoon is weak, and when the other phase, La Nina phase, monsoon is stronger. And so there is a negative relationship. But that negative relationship appears to be changing with time, and it fluctuates. So the association in ENSO gives us a basis for predictability, because ENSO is a slowly varying phenomena, and ENSO is predictable by using coupled ocean atmosphere models. We can predict ENSO. So if ENSO is predictable, and if there is a strong relationship with ENSO, therefore monsoon should also be predictable. So that is a basis for monsoon predictability. But the problem is that this is not stationary relationship. It actually fluctuates quite a bit, and sometimes it is less, not statistically significant, and most of the time it is significant. But this fluctuation makes it difficult for using this as a predictor. But in the recent years, it was shown that this relationship is becoming very weak, and so people have been worried about that, well, monsoon may be becoming less predictable and more difficult to predict. Fortunately, we have actually done a recent study showing that this actually is not quite correct. It is due to some issues with SST as predictor, and also ENSO definition. The ENSO is we are using all the ENSO definition for Pacific region, using some SST in the Pacific region. But the teleconnection and simultaneous teleconnection does not take place only with SST in the Pacific. It also affected by SST in both Indian Ocean as well as in Atlantic. So at a given time, the strength of the monsoon is determined not simply by this Pacific SST, but also can be driven by SST in the Indian Ocean. So we have defined a new definition of monsoon called global ENSO. And using global ENSO, we are able to show that this is not correct. And this actually is not changing. It's a very interesting new result, not even published. And monsoon is just not changing with climate change. And it is very stationary. So that is a very important big result, which is, I'm not going to get into detail, but here what we had shown is that interesting thing my colleagues found out at IISc. They found out that most of the non-ENSO years, drought years, are associated with anomalies, very strong anomalies in the North Atlantic. Whereas ENSO years, of course, ENSO and drought years are associated with, of course, Pacific strong anomalies, but non-ENSO drought years, because many of these, so these are these ENSO years which are drought, but there are many years which are droughts but not associated with ENSO. Then what was producing those big droughts? So that was a big question for a long time. So then, in a time scale of about a month, and they keep generating in the equatorial region, and then keeps propagating like that, and that is how the monsoon intra-seasonal effect within the season affects monsoon rainfall over India. So, and then we have now defined that in a sort of, we have done a lot of work on this, and then one of my students developed a real-time monitoring index for this, and then we can really monitor it real-time, how it is, just like people do for MJO. we can monitor monsoon intraseasonal oscillations, and then it has an outward propagation. We can actually monitor every day how it happens. So I'll not spend too much time on that. So that is the kind of give a little background on what is there in interannual variability, there are intraseasonal variability. These are two big variability of monsoon, and we need to understand them in order to predict seasonal prediction as well as weather, because these intraseasonal oscillations affect the weather. So what we did recently, we looked at how the climate change is affecting the all India as a whole, and what is the climate sensitivity as of the mean rainfall. So we found using that long data that we because we cannot estimate climate sensitivity by using a very short data because of the multi-decadal variation. Because if we do take some short data, that trend is affected by the multi-decadal variability. So you must have a long data. And so we did that, and we removed the effect of oscillations and estimated that the monsoon is actually overall it's increasing at the rate of about 4% per increase of 1 degree global mean temperature. So that is something that we found, and there is a physical mechanism of how it happens. So, however, when we looked at it, in Northeast, so we created a similar Northeast time series, and first, again using these two different data sets, and there we find that monsoon rainfall is actually decreasing in the Northeast, and decreasing almost at the rate of about 3% or less, more than 3%, something similarly like the all India. All India or Central India goes similarly exactly. And Northeast is decreasing. So we were just worried, but for the Northeast we had a very big problem. Until then, in the Central India, we have a lot of data for extreme event analysis, for extreme event finding the frequency and intensity of extreme event. But in Northeast, we have very few data. IMD, in 2010, we tried to look at extreme event in the Northeast. We found only about 14 stations maximum to have 30 years of data, daily data. Beyond that, there is no data. So we cannot estimate trend from that. I'll talk about that in a little later. But so what we did, we actually created a Northeast data over a long period of time. So about 24 stations. So IMD stations only, but there are no data. But then how do we fill them data? So what we used, we augmented them from the in this region, there are a lot of tea gardens. It's a very old history of tea garden. And the tea gardens need rainfall information. So some of the older tea gardens are maintaining their rain gauge and keeping the data in ledger. So my colleague in Cotton University, with the help of students, we have collected all the data from these and created a full 90 years of daily data on this region. And then based on that, we have looked at sort of sensitivity of extreme events in this region. And that seems to be, intensity of this is increasing at the rate of about 12% per degree increase of, and that is even larger than the closest clapeyron. But it is slower than in the Central India. Central India, it is increasing even at 20%. So we have done that study earlier. So interesting. So there is things are happening differently in Central India and Northeast, and why? And that is why. So this is these are some studies we have done here in cotton. Okay, so that is why so this I realized actually there is another schematic here which somehow got mixed up. So this told us that that there is something happening in the changing, and the trend is changing, negative in the Northeast and the positive in the Central India and Northwest. So we looked at that trend. Actually, I don't have it here. That this is it happened. It is found that this is actually projection, but it is similar in observations also. We find that in the northeast, over this region, the trend is decreasing, and in the northwest and central India, it is increasing in the seasonal mean. And so, what does it mean? It means that actually the main monsoon system is expanding towards west. So, in the northeast, is already very heavy rain. It 10% it decreases. Even if it decreases 10%, we have still heavy rain. It's a good lot of rain. But in the northwest, there is very little mean rain. So even if a 100% increase there makes it a big difference. 70% increase also makes a big difference. 100%, and in projections we find it can increase up to 200%. So big changes are going to happen in the northeast, and this whole thing is expanding. And so and we have a paper on Earth's future on that. So I'll again not go. So that is very interesting finding, and that is mechanism why it is happening. There is a very slow, low frequency stationary wave in the upper atmosphere, which produces conducive conditions for suppresses the rainfall in the northeast, enhances the rainfall in the central India. That is why, or the western part of the India. This is done by my postdoc Rajesh. So let me go to the next. So this is, I think, interesting part of the discussion here is how on the onset is being affected by the topography here. So this, we have been looking at this for some time, and we are not very, we did not understand why. See, in the northeast, if I take the annual cycle of rainfall, so this is the central India annual cycle rainfall, this is the northeast India annual cycle of rainfall. In the month of May, this rainfall is larger than this month of June rainfall. And IMD still defines this as pre-monsoon. So I was concerned, and we have been looking at it for a while, and now we understand that we should not call this pre-monsoon, because it is not only heavy rain, it is organized large-scale rain. It is not isolated rain like in the pre-monsoon. And I'll show you the evidence of that. So this was some evidence of that was there. So if onset takes place in May, that the length of the rainy season in the northeast is longer than the length of the rainy season in the central India, right? So this is a study by some people, Mr. et al. And there he was in Miami University or something. They're using the annual cycle of daily rainfall at each location. They defined a local onset. So most of the onset definitions today, everywhere, even IMD definition is a local onset. You take the annual cycle of rainfall, you take a threshold, and you say that if it reaches, and if it persists about more than 5 days, then you consider it as the onset. But more than 5-day persistence can be due to synoptic events, and therefore the local onsets does not guarantee the persistence of that for a long time, because then there can be not only a short break, can be a long break, because that is why the local onsets are affected by what we call a bogus onset. So we needed a definition of large-scale onset. So we argued that. So how do you define the large-scale onset? So this is a study that our student, this is Hemanta Das, he had published a paper in QGRMS recently. So here in this study, what we looked at, first looked at the nature of the rainfall in the month of May. Is it? So if you do that, plot the daily rainfall over the northeast region, it has a very large sort of, it happens just like June rainfall in central India. It has episodic, sort of, it happens in spells of heavy rain, then spells of dry conditions, spells of heavy rain, and like that. And this spell appears to be in a quasi-biweekly mode. So in fact, that is what. So then we looked at these spells. Okay, where does this spell come from? How does it evolve? So if you look at the evolution of this spell, suppose I take many of these spells and see from the beginning to the end of this spell, how are they organized? Are they very much local, or they are organized. So if you do a composite of those spells from the day one, from day one or minus day minus 1 to day 1 and so on, and day 2, day 3, like that, it turns out that it starts organizing around the mountains. Then you see they organize along the mountains and becomes a band. And they are organized, and then finally there are 2 bands, and then sometimes there are now there are more than 1 band, and here also there is mountain. So there is a large scale organized. And this could not have happened if there was only sporadic thunderstorms. Thunderstorms can be very small scale, and and the amount of rain, average rain, you see more than 7 millimeter per day. That is quite large rain averaged over a large area, and it does not happen by thunderstorm, averaged over that large area. So that is the reason we are saying that something makes the rainfall organized in. And how does it get organized? And that is where the next step. So it can be organized. So, but at the time of May, what produces the organization? Normally, what produces organization? ITCZ produces organization, and because ITCZ is in a very large scale. Then synoptic events like low pressure systems produces organization, but there is no low pressure system in May. There is no depression, no ITCZ. But what produces the organization? We found out that it could be organized by 2 mechanisms. One is that all you need is a low-level vorticity. So if you have a low-level vorticity at 850 millibars, strong enough to push the wind, push the moisture up the mountains, that will produce convection. So you need a relatively strong low-level vorticity. But where does this low-level vorticity come? It seems to come from 2 sources. One is this QBM, quasi-biweekly mode that propagates from east to west. So this QBM comes from this side, and the composite of this QBM shows, sorry. So if you plot this QBM has this equatorial Rossby structure. So when this QBM comes over there, these winds interact with this mountain, and convergence of these produces this heat source here, the rainfall here. So if the point is that during summer the QBM is centered around 10 degrees north, and it produces a Rossby cyclonic vorticity in the north, and that cyclonic vorticity is close to the northeast and produces can produce a convergence and produce the initial organization. Another way is extratropical waves. Extratropical waves can intrude let me show you the other way. There are a lot of other evidence that it will. How much time I have? Other evidence. The other way is that see if I take the vorticity, average vorticity over this northeast, in the month of May. In fact, even it's all the way from January, there is a stationary vortex in the month of it's a quasi-stationary vortex in a very large scale. So there is, but that vorticity is not very strong to produce this. It is a cyclonic vorticity. It is positive. Okay, cyclonic vorticity is not enough to produce the organized convection. But at the time of onset, this vorticity is increased by a factor of 3. And that once it is done, then the organization takes place. And that organization is assisted by this moisture flux in this region increasing by a factor of 7 or so, and so on. And that is a time when the tropospheric temperature also changes sign. So all this kind of happens simultaneously because one is related to the other. So and that we believe is partly due to the extratropical Rossby waves, transient Rossby waves. So there is a stationary Rossby wave sitting there, it is producing a ambience. Then on the top of that, a transient Rossby wave passes by, and that extratropical Rossby wave has, suppose I put here average potential vorticity, average over the top from the top to the bottom, and with height and time with respect to the day of onset. If I do composite, what I find is that at the time of onset there is this negative potential vorticity intrusion from the top to the lower atmosphere, and this lower atmosphere negative intrusion of vorticity. So cold air is coming. The cold air sinks, produces negative potential vorticity, and that produces, therefore, vorticity conservation forces relative cyclonic vorticity at low level. So this low level cyclonic vorticity enhanced suddenly, because extratropical system can come and force potential negative potential anticyclonic potential vorticity will produce cold air. The high pressure system, cold air is sinking, and that cold air sinking produces a potential vorticity intrusion to the to lower level, and that produces a generation of low level cyclonic vorticity. On the top of the mean, that enhances the vorticity by 3 or 4 times, and then you can start producing convection. Once convection is generated, it will self-sustain, because it will produce a heat source. Heat source will then produce more moisture conversion. Moisture conversion will then sustain itself. So a transient Rossby wave can also, and we have found out that about 50% of that is due to these, and about 50% of that comes from the westward propagating QBM. So there is a physical mechanism by which organization can take place. And that is why we suggest, we say that is a very, I think, enough evidence that actual large-scale onset does take place in the middle of May. But it is now, we have now another study, which is, I'm collaborating with people in the IIT Madras, and there is a master student, Yogendra Patel. He has done a study using climate network. Now, climate network, complex climate network. So what we do, is that, you know, all the local, as I mentioned, so far all the definitions are local, based on local onset. And local onsets are affected by synoptic disturbances, are not reliable. Their forecasts are also not reliable. So we first tried to define a large-scale onset. But how do I define large-scale onset? I need to include large-scale vorticity. But large-scale vorticity, for a long time I was trying it and I was not getting an idea. But collaborating with these guys, we found out by using this network, we could separate the large-scale. What is large-scale onset? Large-scale onset means that monsoon is a planetary scale phenomenon, so it is much larger, ITCG scale. So it is much larger scale. If there is onset takes place, everywhere onset must take place. That means onsets must be connected in the large scale, interconnected or simultaneous at the large scale. And so the climate network, what it does is looks at, using something called proximity network, you look at clusters of local onset. You start with the local onset. Local onset data is there, either from IMD or from Mishra et al. And anybody. I can use the local onset and then go on finding when local onset takes place, okay? And then see when they are connected. So, and what kind of clusters, how do clusters grow? So what we are proposing is that local onset, local onsets are connected by the organization of the convection itself, because convection gets organized in these 3 scales. Well, it starts with the mesoscale, because mesoscale organization, within a synoptic scale there are mesoscale structures. They get merged and they becomes a synoptic scale. Initially it starts with a mesoscale, then another mesoscale form, another mesoscale form. This mesoscale clusters becomes a synoptic scale when they are connected. And then, suppose more than one synoptic scale disturbances get connected, they become a planetary scale structure. So it is essentially, we know about this organization, but this complex network, without any external intervention, automatically separates it out. So, and that is what in this you see, okay. Oh, how do I? The bar, what happened to the bar? There is a bar which I want to control.
This one.
No, that I know. Let's go back. इसमें बार एक बार होता है ना, what is the bar? ऐसे. I'm that is how to roll actually. That is how to whistle. Okay, so okay, here it is playing now. All right. It is playing. All right. Okay, but I cannot control it. But I'll tell you what. Play it again. Play it, please. Arambhanipura.
This one is the bar, sir.
Huh?
This one is the bar.
Which one?
This one. This black color is the bar.
Oh, black color is the bar?
Yes.
Okay, let me see. But where is the... no, it cannot be. Okay. If I... ever correct this. Hold on. That is good. It's okay. See, now it is beginning to start in the northeast, and then it is going very fast. Okay, so I cannot control it, but I could have shown it better. So what happens is, it starts here. Sorry. Now it is withdrawal. So withdrawal, it just goes like that. Okay. So what happens? It starts with a small mesoscale events in the month of April itself, in the early May, and then they grew into some kind of a synoptic structure, not quite big, but as they, and then there is another one starts here in the southeast Asian monsoon, and these two things merge. And when they merge, it becomes a planetary state. And that happens in the first, what is called abrupt transition. Abrupt transition takes place around 18th May. And that is when it becomes, onset takes place in the northeast. The first large-scale onset takes place. So first large-scale onset takes place only in the northeast. First. Then it propagates, this whole thing, new onsets get added up, and then thing propagates towards central India. And by that time, there was one synoptic scale, mesoscale started here, and that grew into a synoptic scale here, and then, but it was still synoptic scale, it was not merging with anything else. So, but when this big thing came here, and then it became a little bigger, these two things merged. And that is when a new second transition takes place. And second transition is the large scale onset in the South India, or in the peninsula. So, and after that, they move, then the large scale onset has taken place almost everywhere within that boundary, and now they move to the western, they sort of expand to the west. So, this is, this gives automatically, so here it is kind of surprising that first onset takes place, large scale onset takes place in the northeast, and Kerala is actually later. But it is correct because after this onset, what happens? You are guaranteed that the rainfall will persist because northward propagation. What happens? These local onsets sometimes selects see there are these northward propagating pulses of the monsoon intraseasonal oscillation. But many times the monsoon intraseasonal oscillation comes to 10 degrees, and then the onset declared, but that the North India is not ready for northward propagation, so it doesn't propagate. And then you have already declared onset. Now, in our case, the large-scale onset after definition, it never takes up the first spell. Sometimes the second spell will definitely propagate. By that time, because of the onset is taking place already in this region, the large-scale condition is such that northward propagation will take place. So northward propagation is guaranteed. So that is why we believe that this is a better way of defining onset, and hopefully that will. So here the important organization, the role of topography is very important. So let me show in the last part. How much time I have? Last part. So last part is related to these extreme events. Okay. So about 10 years ago, 10, 15 years ago, we tried to look at extreme events in this region, and as I mentioned, only 14 stations were there, and we found that the extreme events were decreasing. We published this result because, but we are not. This trend was not quite robust, because we did not know whether it is decreasing or why decreasing was also not clear at that time. It was consistent with the thermodynamic conditions, but is it a real trend or it is due to some multidecadal variability? We did not know. So we wanted to understand the multidecadal variability, the extreme event trend over a large data set. But that was not available. But as I mentioned, we created this data set now, and we have done that recently. But at that time, we looked at something about the dynamics of this onset. So what we did, we looked at it. So we took all these 24 stations, and the day of the extreme event, we took 1 day before and to 1 day after, and took a 3-hourly outgoing long wave radiation, the convection structure, and did the composite. So something very interesting emerged. So it starts with a mesoscale disturbance, and then mesoscale disturbance intensifies and propagates a little bit south and becomes intense, and that is when the extreme event takes place. So if we did that and then put a sort of do a composite structure of this, so this so this size of this mesoscale event is about a couple of degrees, about 200 kilometers. That kind of a size is this sort of. So it is kind of a mesoscale system. So if I do so there is an indication of southward propagation. So we did a little bit of 2 degree longitudinal average, and you did a lead lag composite around that location. And so it turns out that this southward propagation is, and the periodicity is about just a day. So this is a relatively periodic kind of an oscillation. That oscillation seems to be generated. And what kind of such oscillation takes place? It is probably not just it's a diurnal like cycle, but it is like a oscillation has a certain scale. And it turns out that is most likely it is some kind of inertial gravity wave which is generated by the winds associated with the mesoscale disturbances. So in this, so there is a high vertical velocity here, low vertical velocity here. So whenever this velocity is high, that is when it over the ambient large scale environment that produces an extreme event. So this is definitely again something that is the dynamic and interaction with the topography creates oscillations which can enhance and create the environment for an extreme event. So this we knew, but now, now recently we have done actually in the next talk, I'll take in more detail how this multi-scale interaction, because the mesoscale things happen over an environment of a synoptic scale. The synoptic scale happens in the environment of a planetary scale like MISO or MJO or ITCG, and then this multi-scale interaction is ultimately determines where the extreme event is going to take place, and I'll talk about that in detail in the next talk. But so essentially, you see that this topography has very important role, not only on determining the onset, for example, because without the topography, onset would not have taken place in May, no way. And that is a very large-scale dynamics. And even in the extreme events, it has a very important role in making the more intense and more frequent in this region. So, therefore, I'll stop here. So it is the Northeast is essentially a special place in Indian meteorology. It has a national laboratory to study this kind of a scale interaction between convection and large-scale dynamics. Yet, unfortunately, Indian meteorologists have been sort of failed to pay much attention to these, and I suppose it is understandable because it seems to be a small region in the global scale, or even in the Indian region, large-scale regional scale. It's a small region, how to border. So I said that we only have to study because nobody else seems to be studying this. So that is why we have started doing some of this work. And it is fascinating physics, new interesting interactions we are learning from that. So I think it has been very fruitful. Unfortunately, in our region, this observing network is very poor. It has been a very big problem. And I'm sorry, but I don't see much of a comprehensive plan to make it better. And that is where I think this radar. But more importantly, another problem is that, as Professor Chandra will probably say, we need to create, even if we have a lot of radars here, estimating the QPA in this region will be very different from another region. So I think that is where is going to be a lot of research has required, and there is nobody to work here. Nobody has worked here, and so I think in our country nobody has worked in kind of an environment. So I think we need a very clear plan to do that. So I believe a well-designed network will be very valuable in this large-scale interaction studies. But but the radars themselves are not going to help much to study and understand the dynamic unless we can derive the products, research quality products can be derived out of them. And that is where I think we are missing expertise, and we need to build that expertise. With that, thank you very much, and welcome again. Any question? I'll be happy if there is any. We have time. What is the tea break? Okay, I'll be very happy. Any question?
Sir, in the beginning slides, you saw that extreme events are increasing, but overall mean monsoon rainfall is decreasing.
Correct.
So is it connected to some propagating, whether these extremes are embedded within those LPS, that's why it is propagating even though frequencies are there, but overall?
No, I think you don't need that because the moisture content is still increasing. Even though the mean rainfall is decreasing, yes, the moisture content at the level is still increasing because that is local. Okay. So moisture content increase means that locally instability is higher.
Okay.
Even though so the extreme events are governed by very local dynamics, local instability. Yes. And local instability is still strong, and it can still increase because as moisture content increases, instability can still increase. But large-scale rainfall can be affected by large-scale circulation. Okay. And that large-scale circulation has a weak high-pressure system subsidence sitting on it. And that subsidence makes the large-scale decay, but not the extreme events. Extreme events are locally happen. That's not affected by the large-scale dynamics. Okay, but the large-scale average rainfall will be affected by large-scale dynamics.
Right, so it can suppress. And another thing, like northeast region, it is well off north from 20-degree latitude. So if we see fundamental of it's a beta plane approximation, So this quasi-geostrophic approximation, it can be valid in that region.
Yeah, it is. This is also because of that. It is an interesting area. It is neither fully geostrophic or neither fully tropical. So it is in the boundary of tropical and extratropical region. That is why sometimes the interaction can take place, and that is why I have shown you an example of interaction is this intrusion of extratropical waves, and that can happen in the sort of around the kind of May. But by June, if you say the jet stream has moved farther to the north, and this intrusion will not come to. So just around April, May it can happen, and that is May is the time when this intrusion can make a big difference. Beyond that, what will happen is, see, this can happen only through the upper atmosphere, because there is this big topography shaping. So so upper tropospheric, there has to be a big cold wave going through.
Sitting over there,
So, and that then must, just now in the last few days, I think last week or so, we have cold all over the country, and that is probably because of a large scale this extratropical system. That is because the polar tropospheric system has affected all this. So all that cold air is coming and sinking on us, and that is why it is enhancing our cold, and that is what can happen. And a very large thing can happen in the month of May, and that people have known before, but we did not really realize how it affects the onset.
How to quantify whether those extratropical intrusion in the upper layer, it is creating more instability, or local synoptic scale, this quasi-geostrophic things can generate thermal instability. So which is dominated?
Agreed, because at that time we don't have any systems. Hydrodynamic instability, there is no chance. So see, local instability has to be generated by hydrodynamic instability, like barotropic instability. Right? The wind shear can produce barotropic instability, but at that time there is no ambient strong wind shear. So there is no instability. Low pressure systems are not there. So that some disturbance has to create that low pressure, but that hydrodynamically it is not possible at that time. But if somehow, but there is a weak cyclonic vorticity is there, but that is not sufficient to produce instability. Now, transient disturbance comes, it enhances this by 4 times, then mechanically it will produce an organization. That's all. It's no instability. No instability. It is almost like extratropical forced convection. That's all. So it is dynamically it is between tropical and extratropical. Extratropical, everything is forced convection, right?
Yes.
So here we are mostly, it can be free convection, but in this kind of interface, sometimes you can have forced convection if the orography is properly is in the right place in the right time.
Right. Thank you, sir.
Sir, very thankful to you for this presentation. I have a small thing that unlike the onset in the Kerala, then what could be the parameters in case of Northeast, that if you kindly briefly tell this, that parameters?
So all that same thing you can have, you can almost everything. I have shown you one figure where the northward sort of, see, one of the parameters that we use is the 850 millibar wind westerly jet strengthening. See, again there is the sort of jet or winds, whatever you call it, wind speed enhancing at the time it jumps by about 4 times, 5 times. So this is always related with the organization of the convection. If the convection is not organized, it is not accelerated. But if it gets organized, it will accelerate. And this organization takes place, so we have shown that over Bay of Bengal, instead of Arabian Sea, don't look at Arabian Sea, you look at wind strength over Bay of Bengal. If the Bay of Bengal wind strength exceeds certain value, then you can use that. And the moisture transport also enhances northward transport of moisture. The winds are always, in the month of May, mean winds are still like that, westerly, southwesterly in that. And then I have a lot of data and how it changes that, enhances that. We have done composite of large scale winds and how it suddenly becomes very strong this way. Earlier it was very broken before onset. And then suddenly, due to the organization, the whole thing becomes very large, all the way to the Bay of Bengal. So winds you can use moisture transport, and the tropospheric temperature. All these things are, I think, can be guiding as. But you don't need. Now we can do a real-time monitoring. This methodology can use real-time monitoring if we have the analysis that is available on a daily basis that IMD produces, and we are requesting IMD to cooperate and give us this, so that we can produce a real-time monitoring of this onset everywhere, large-scale onset. So that will combine everything. But rainfall itself is sufficient, and then you can have backup, like how the winds are also changing. So you can combine both and confirm yourself that the onset is taking place. So it is more all the parameters that you use for local also is satisfied here. But over the Bay of Bengal, you don't have to do it over. And when large scale onset over the peninsula takes place, of course that acceleration will also be there.
Okay, sir. Thank you, sir.
Thank you, sir, for your nice talk, sir. You said from the northeast, the system is moving toward the central India and other kind of the things. So whether those systems are the deeper system?
Which one?
You said that monsoon,
monsoon is expanding.
Expanding. And
expanding, that is only seasonal mean sense I am talking about, not in the weather sense. Weather sense also it is happening. So the mean sense, seasonal mean rainfall is expanding. If you take a seasonal mean, a sort of isochrons for different decades, and that isochrons are kind of expanding to the west in the recent decades. That is why we are seeing now, all that is now seen in Rajasthan, Gujarat. There is more convective systems, more rainfall, and so we have also shown that now the low pressure systems are entering. Earlier, because of the situation, it used to be by about 70 degrees, it will not go. Now it goes to 60 degrees.
That's true. No, so the thing is why I ask this question, like the small system, like from Bay of Bengal, it's propagate northward. Small system means like less than 1,000 kilometers square area convective organization when you see from this radar. But the bigger system, it moves towards the southern, means towards the Bay of Bengal. So towards the Bay of Bengal. The small system moves this one, okay, and the bigger system moves down. So whether
low pressure.
Not low pressure, sir. Like with the Kolkata radars and other radars, so what we have classified like areas.
The movement of those systems are like movement of tropical cyclones, right? So they are affected by beta effect and the steering current. So you have to use both, and depending on that particular condition, I won't be able to answer that correctly because I have to see what is the ambient circulation at that time, and then what kind of steering current you have, and what is the beta effect. These two effects will produce their propagation. So something like that. Also, in the very large scale, even the heating, the rainfall. See, rainfall is produced in the west northwest sector of in the low pressure systems, right? So when the rainfall is concentrated over there, it produces more heating over there, and locally it produces a anomalous cyclonic vorticity. So that large scale vorticity is affected, is changed by the local vorticity, and that can also make a additional movement, add to the movement. But very strong tropical cyclone, that part is not very, the other dynamical effects are more strong. But in a larger scale like depression, I had written a paper long time ago in 1988 in Nature. So we have shown that the convective feedback itself can produce a west-northwest propagation. So because heating will produce anomalous response. The anomalous response will affect the vorticity, and the vorticity advection will then make change the propagation.
Okay.
Sir, very interesting talk as always. 2 points I want to make. Firstly, in your presentation, I did not see anything of the discussion of the anticyclones of the Bay of Bengal and Arabian Sea. That creates the dry line situation, which basically, when you're talking of the tropical Rossby waves, equatorial Rossby waves, when you're talking of that, pushes that anticyclone, and its location basically decides the movement. So that is the primary driver for convection for operational meteorologists like us. Pre-monsoon convection is decided by the location of that anticyclone, and it's strengthening and weakening. That I did not see here. That is one thing. And
I think that pre-monsoon, the anticyclone is part of some of these systems. What is the system that is anticyclone is associated? I'm not sure. I have not really looked at it that way. But see, it is equatorial Rossby waves will have an if it is it is sufficiently to the north, then it will have anticyclonic circulation in the northern part, because north of the equator it will be anticyclone because it is going this way, or I don't know exactly, but we have to look at it more carefully. But anticyclone must be part of a system. But what kind of system? Is it the QBM or something else?
It is quasi-stationary. During this season in the Arabian Sea and in the Bay of Bengal, below 925 HP, we have a anticyclone sitting in both the Bay and the Arabian Sea, which is favorable for creating the dry line, that Bengal and northeast, that line kind of figure that you showed.
What produces that? Is it the surface heating of the land or what? Most probably surface heating of the land.
It is basically the surface heating of the land.
Right. It has to be,
so that basically moves due to this equatorial Rossby wave.
Okay.
It is pushed northward, and then it pushes the moisture into the.
So that is in our that is already there in our sort of mean conditions. So on the top of that, we have these. So we have the equatorial waves are on the top of this mean. That is why it is extended to the at 10 degrees north, around 10 degrees. If the equatorial wave did not have a mean to work with, then the equatorial waves will be centered around, the Rossby wave will be centered around the equator. Okay. So the dynamic equator is affected by the large scale, this anticyclone that you are calling is affecting that position. And so that is already there in our sort of background, in the background state. So if it is stationary, it is a background state of the month of May, right?
So then it doesn't come as a monsoon, like monsoon is large scale. Ramage's criteria says large scale change has to happen. Right. The entire wind direction has to change and persist. Does it happen?
It happens. That is exactly what it happens.
But again, that happens also because the jet core moves to that location and it's quasi-stationary, and that I mean these two, upper atmosphere, that extratropical Rossby wave and jet core moving to that location. So that really is a change. For my point is, it's a change of 3 to 4 days or 5 days at a time, not that large scale change, is it, sir?
It is. I can show you how the large scale is maintained. I have a lot of figures and diagrams, and I'll show you how large scale is maintained. Every time after the large scale onset, it is maintained. I'll show you many figures I have. So I can show you sometimes if you have time. I'll show you some more that I have. So it is guaranteed that the large scale will sustain. Okay, anything else? Anyone? How about students? No? Okay. All right. Thank you.
Thank you so much, sir, for your insightful session on Indian monsoon and Northeast monsoon in particular. So we will break for a small cup of tea, and we'll be back here within 10 minutes, 12:10, and we'll move to the next session. There's also a small announcement. Participants who are yet to register can do with their registration at the registration desk set outside the hall. Thank you so much.
solution. Now active at IMD Guwahati, it supports continuous atmospheric monitoring. Samir proudly launches its indigenously developed atmospheric radiometer system, a cutting-edge ultra-sensitive passive receiver for atmospheric.
Hello? Yeah. Ulta. What's wrong with that? No, I don't. I want it here. It's okay. Why? Hello? Oh, it's okay. Hello? हेलो हेलो उधर ठीक है अगर प्रॉब्लम होगा तो आई विल स्विच टू दिस You want this?
Welcome back. It gives me immense pleasure to invite our esteemed speaker, Professor Chandrasekhar, who plays a key leadership role as co-PI of the CSU Chill Radar Facility and as Deputy Director of the NSF Engineering Research Center, CASA, where he leads the Sensing Research Trust. He has also directed the prestigious research experience for undergraduate program at Colorado State University. He was elected Fellow of IEEE, the American Meteorological Society, and CIRA in recognition of his contributions to quantitative remote sensing. He has served on National Academy of Sciences panels, Future Radar Systems Beyond NextRad Flash Flood Forecasting capabilities at Sulphur Mountain, California, and has held as visiting professor at the National Research Council of Italy and distinguished visiting scientist at the NASA Goddard Space Flight Center. His numerous honors include the NASA Technical Innovation Award, Abel Outstanding Researcher Award, CERMAC Outstanding Advisor Award, Distinguished Minority Service Award, Dean's Council Award for Excellence in Teaching and Research, Halliburton Young Faculty Research Excellence Award, Vesala Distinguished Fellow, and Abel Outstanding Research and Graduate Program Award in 2004. He holds a BS in Electrical Engineering from IIT, MS and PhD in Electrical Engineering from Colorado State University. Professor V. Chandrasekhar is internationally renowned for his pioneer work in polarimetric radar observations of the atmosphere. With deep expertise in radar system design, radar network development, DSP design, and RF communication systems, he has significantly advanced weather radar technology and its applications in atmospheric science. His research spans image processing, neural network applications, and large-scale system simulation, and he has organized and participated in 6 major multi-agency national-level experiments involving radars, aircraft, and ground instrumentation. As an active experimentalist, he conducts specialized experiments to collect in situ data for validating new techniques. He is also the author of 2 textbooks, Polarimetric and Doppler Weather Radar, and Probability and Random Processes. He has served as PI and co-PI on major national programs including NASA's TRMM and GPM missions, the X program at CSU, and the DARPA NGI program. With these words, I would request Dr. Bandana Chaudhary to felicitate Professor Chandrasekhar with a Fulam Gamusa. Sir will be delivering his talk on microphysics, precipitation processes, and dual polarization radar. We look forward to your session, sir.
Thank you. And, I am a professional teacher, so I'm going to behave like a teacher here. So all the people sitting in the back, if you're really interested in this, please come forward, because I want to be able to see you. So please, because this is not a movie theater, this is a regular class. So, and I will stop in the middle and ask questions. So if you are watching your cell phone, you will be embarrassed. So, unless you have these people in the back, come forward. That gentleman is not even listening to. Come forward. Okay. Can you all hear me? Yes? Because this is, I am standing between you and your lunch. So I want to make this interesting. Is that gentleman in the class, or he's not even, he's not in class? Okay, then he is excused. Okay, so a lot of the stuff I'm going to talk about is what we call as textbook material. And so there is a polarimetric radar textbook that's been around for a while. But people have told me that's very complicated. And then they asked me to write a simpler book. But once you have written a book, you know how much work it is. It's a lot of work. So once you write a book, you say never again. But then after 15 years, then you soften up. And then I wrote a simpler book with a lot of conceptual diagrams. So a lot of the material I will present here is from that book material, so we will go with that. So this is truly from the perspective of, like the secretary said, capacity building, so that a lot more people are knowledgeable about weather radar. So with that introduction, so this is the book where this is the newer book of our textbook, from which a lot of the figures I show, and then a lot of the information I will be presenting today will be from that book. Okay? Has anybody seen this book? Oh, good. Some of you have seen it. Okay, good. Okay. So this talk will be a radical shift from the previous one, which was looking at many things at the global scale. This is going completely into micro scale of precipitation, microphysics, and then building the connection to radar. And I have, is there a clock? Okay. I'm not sure how far I will go through in this 1 hour, but we will just end at the end of 1 hour, whenever it's 1 hour, and then we will just deal with it. So the microstructure of precipitation comes from many things. This is particle size distributions, and then the particle shapes, because the scattering from these particles is what contributes to the radar signatures, and the fall velocity. So all these things control. I think we should close the door because it's making too much sound. And then this also connects to processes. It's the physical processes that are seen will be observed by the radar, and that is another thing that I will show you how to look at this. How many of you in this room have had any access to some polarimetric radar data, or you're going to see this for the first time? For anybody who's seeing this for the first time ever with no exposure to polarimetric radar, please raise your hand. I have 1, 2, 3, 4. Oh my God, okay. 10. It's good news and bad news. It's good news because if you're hearing it for the first time, you're learning something new. So I'm not teaching this material for Subrata Das, who is an expert in this. So this is for new people. So if you feel it's too basic, don't feel insulted, okay? So warm rain process, and warm rain process is based on collision, coalescence, breakup, evaporation, and size sorting. All these things are basic microphysics of precipitation, and which you should be able to see it with radar. And then the cold rain, which is due to vapor deposition, aggregation, and riming. I'm not sure how much interest is there in cold rain in India, but when we will get to that if we get to it. Okay, and so that cold rain happens when you go further up into the Himalayas, and so then we will also classify precipitation types. We will talk about stratiform precipitation, where there is a nice melting layer and then the bright band. And then there is this orographic enhancement, which is happening all over India, and it is also responsible for flash floods and which is defining the precipitation in complex terrain. And it has got huge societal impact. And then you have convective storms, which is it's got updrafts, it's got ZDR columns, and it has got hail, and there is a lot of that happening in the plains in India. So how do we observe all this microphysics from radar is what we will see. Okay? And at any time, I will stop and reciprocally ask questions. Are you with me? Do you understand what I'm saying? And so on. Okay? Okay. And also, this is supposed to be a class. So in the middle of the class, you can raise your hand and ask a question if you are not keeping up with me. You understand? So you can, in the middle, raise your hand. So, because this is, oops. Okay. Particle size distribution. So this is a radar volume, okay? A typical radar, you see, it has a 1 degree beam, okay? And 1 degree beam, and let's do some simple math. 1 degree beam, if you go to 60 kilometers, do you know how wide is the beam? The simple formula is what? The arc is r theta, okay? So 1 degree beam, if you go to 60 kilometers, is 1 kilometer. So there are lots of raindrops in that beam, which is 1 kilometer disk. And then the thickness is about few hundred meters. Okay? So a few hundred meters is how long is this room, do you think? Back to front. It's about 100 meters or less. So it's twice that size. And then you can guess a kilometer. That's how big it is. So a weather radar gets signal from all the raindrops in this volume and puts it in one place. This looks big for us. For microphysicists, that is big, which is small from a global scale observation that we were seeing in the earlier part. So once you have collected all the raindrops in this, you can sort them in size bins. Just the way what I can do is, I can go around the room, ask people to line up, and then do a distribution of the height of these people in this room. Okay? We will see a distribution between, let's say, 4.5 feet to 6 feet and few inches. Right? There will be a distribution of the people in this room. So similarly, I collect all the raindrops and then sort them out. There will be a distribution. And what people have done is, over a period of time, they have tried to plot it, and they have saw that most of the raindrops pretty much fall between 0 to 6 or 8 millimeters, depending on how they got formed. And then there is large number of small drops, and then there are very few large drops. And why is this important? Because the volume of rain is proportional to d cube. So please come forward. Come forward. That's the rule. Yes, thank you. So volume of raindrops is d cube. So it takes 1,001 millimeter drop to give the same amount of water as 1 10 millimeter raindrop. It's d cube, right? Are you with me? So similarly, the radar signal is approximately proportional to d to the 6. So it takes a million, if there is a 10 millimeter drop, it takes 1 millimeter raindrops to give the same radar signal as 1 10 millimeter raindrop. That's what you need to understand. Or if you keep it as a 5 millimeter raindrop, then it takes about 625 1 millimeter raindrop to have the same amount of water as a 5 millimeter drop. So there is strength in numbers, but volume rules the place here. So I want you to get into, the depth and understanding this. Now, we are not sure if just for convenience this gamma distribution got done, because there is a lot of times the small drops evaporate and then there is like a little fall in the distribution. Whereas for ice crystals, historically people have just stayed with an exponential distribution, and then the ice particles get large. I mean, you don't have to go to Alaska to find ice. Right here, if you go up, there is ice. So if you have a radar, you just scan and it will show you directly. There is ice in Pune, there is ice in Chennai, no problem. If you go up, there is ice. So just because we don't see ice on the ground, let's not think there is no ice aloft. That's something that I want all of you to remember. Because a lot of the times people think if you want to deal with ice, you have to go to Himalayas. That's not true. You go up, past the melting layer, there is ice. There is ice in Chennai. So there is aggregates, which is small crystals that cling together and then form bigger particles as they fall. And yes? said this is all, okay, her question was why it's all exponential and why we are not using gamma. It's not like physics behaves this way. All these distributions is something we create an approximate model to fit the data. Okay? So people have found that the complexity of adding a third parameter is all too much. There is so much unknown. We're not gaining by making this distribution very complicated. So let's just call it exponential. Exponential behavior is the majority of the behavior of these distributions. Okay? She's going like this, which means she doesn't agree.
Yeah, snow has a much more crystalline structure compared to rain. If you're taking shape into consideration in case of rain and not in terms of snow, is
no, shape is the shape of the particle is different from shape of the distribution.
Okay, fine, yeah.
Yes.
Is proportional to the cube of the diameter. That's why larger things are less possible. But for snow also it remains same. The volume will be.
Snow also it is proportional to the volume. In addition, there is one more factor that gives the amount of water.
Okay.
Can you guess what it is? It's very easy. Think. What gives the volume of water? Have you heard about when you melt ice?
Yes.
The volume of
Increases.
density.
Yes, density.
So when you have fluffy aggregates, they are really a very low density.
Okay.
That doesn't amount to too much water. The particle size could be big, but it's when you melt it, it just amounts to not much water.
Okay.
So the density is an additional unknown factor when you go into ice crystals.
Okay, thank you.
Okay, good. You see, through this interaction, something else came. So then let's keep going like this. When we talk about snow crystals and all these things, they fall under the category of what is called low density particles. Then when we go into hail, these come into the category of high density particles. Hail is something that's all over India now. When I remember when I was young, when you see hail, people have to, and also because of this more radars around, more things are being observed. People are starting to see hail, and big hailstorms creates substantial economic damage. In U.S., hailstorms are the biggest economic disaster-creating events. They are becoming much more than floods of late. Because one massive hailstorm will just come create a huge havoc. So because this rain volume sees all these things put together, it's important to understand this. And then why are we interested in the microphysics? So that we can interpret the backscatter signals and then remotely start studying these things, which is essentially the microphysical processes that we are observing. Okay. This is what I talked about as the radar sampling geometry. So this is the slant range, and then the delta R, which is the disk that is being observed, is c tau over 2, and c is the velocity of light. Tau is typically the pulse width used in radars. So what the radars do is, of course, I'm assuming you know something about radars. Radars send a pulse, and typically these weather radars, for all practical purposes, just for the sake of this class, assume it's of the order of a microsecond. Okay? C is the velocity of light, tau is 1 microsecond. You can just do the computation, and then you can figure out it comes to approximately around 150 meters. It's very easy. Okay? And then the cross beam size, That's if it's depending on how far it is. If it's basically r theta, which is theta is the beam width. Typical, this is again general approximation. Typical meteorological radars, the beam widths are in the order of 1 degree. So r theta, when you go around 60 kilometers, is a kilometer. So there is a lot of particles. Now, this is actual plot of lots of observations of raindrop size distributions observed on the ground using disdrometers. Is there some problem? Everything is okay? Okay. They were discussing something pointing to me, so I'm trying to figure out. So, some of the animations may not work because I am running this not from my computer. So, I wanted to show, I actually took a real distribution and distributed it in a box. And these big particles fall faster, small particles fall slower. And then when all these ground-based devices, the way they observe them, they have a laser beam. As these particles pass through them, they have 2 laser beams typically. Looking at the time between the passage, they find the velocity of the particles. And then, depending on how much shadow beam they are creating, they are trying to get the size of these. And then you look at N of D, which is particle size distribution. This is how a lot of the instruments are measured. So, I wanted to champion what Professor Goswami was saying. In order to understand the microstructure of precipitation in this area, especially at different altitudes, some of the simplest and cheapest thing we could do is deploy a set of disdrometers on this region. That will go a long way in understanding the microphysical characteristics of rainfall. So that's one thing that I want to. The RMC person is gone. So if you will see it, I will show you. Maybe you can take this up as a Prime Minister professor. Yes. Yes. Because in fact, if somebody is, I should be very careful what I say in the stage. Sometimes I get very excited and say things like election promise. If somebody is willing to reply in anything, I can actually send a couple of disdrometers. Okay? So I will say that to Gauhati University. Okay. So to come back to your question, this is the actual data that's being observed. What people do is start fitting gamma model, and then just to make it convenient to do some analytical transactions. So it doesn't mean gamma is what happening in nature. People have for a long time looked at log normal distributions to fit all these things. Okay? So this is again the microphysical structure of rainfall. Now, if you get this thing out, you can fit an exponential distribution to the same data. You can fit a line like this. It's just what you choose to fit. That's all. It's to the data. There's nothing more than that. Okay. I want you to see a little bit about the raindrop size distribution, get an internal feeling of rainfall. In fact, long time ago when we were starting to, when you are in a radar room and then you are constantly watching for storms, you get bored. Then you see some rainfall. I used to take a bet. Okay, guess the reflectivity, guess the rainfall rate, because you can visually see rain. Sometimes you see rain, you can just run through it, you won't get wet. But sometimes you can't even see through that rain. But you cannot have as much water. Look to the left side. This is monodispersed ESD, all 1 millimeter raindrop, and this is 1 meter cube. Okay? On the right side, it's monodispersed raindrop at 2 millimeters. But this is also within 1 meter cube. Both of looked at radar displays? When I say 37 dBc, you know what that means? Some of you have. Can somebody, when I say 37 dBc, who recognizes? Raise your hand. Only one person. Oh, 3 people. I'm sure more people know 37 dBc. No? Yeah, it is reflectivity. When I say reflectivity is 37 dBc, you understand that. But online people are YouTube. I'm on YouTube. I have to be careful then. Are you going to post it on YouTube? I have to be. Then I have to be careful what I'm saying. And I hope it's not being recorded. Let me. Hello? Hello? Can you hear me? Okay.
Sir, please, इधर में लगा लो. इधर में लगा लो.
Yeah, but it's very inconvenient. ঠিক আছে? So, now I look like I'm selling something. What can I sell? I sell some disdrometers. So, both of them have same reflectivity, but one has rainfall of 35 millimeters per hour, and the other one is 6 millimeters per hour. So, this is exactly the challenge of measuring rainfall. I want you to understand. I'm making some very serious statement. Rainfall is one of the hardest things to measure. If you go back and look at it in history, people have been trying to measure rainfall from before BC. There you go look into museums, there is all sorts of devices that people have that have tried to measure rainfall in so many ways, because the rainfall information was used to rainfall information was used for so many purposes. First of all, it's rain brings water. That's the primordial element of life. That's important. Second thing is, olden days people thought the kings, people who had more rainfall, they had more crops, so they wanted to tax according to rainfall. So they wanted to measure. There are a lot of reasons people wanted to measure rainfall. You go into Chinese culture, Korean culture, ancient Indian culture. There are so many things that people have used, devices that to measure rainfall. Even today, we are trying to measure rainfall, and then it is a very, very hard problem. Can somebody tell me why it is a hard problem? It's something deep. I want you to think about it. First of all, rain is not a continuous field. It is discrete raindrops that is put together. It is different from the flow of water in a river. The flow of water in a river is a sheet of water. There are so many, it's very simple device you can put there and then measure the flow. Layer sitting here remotely, you don't have to send balloons and all that stuff, but it is still struggling. It is still struggling to measure rainfall. It does measure rainfall at a large scale, and then people start comparing with rain gauges. It has issues because both of them measure at different scales. And so that's why rainfall measurement is one of the challenging problems, and it will remain challenging. Okay. The same 37 dBc, you have one 4 millimeter raindrop in 1 meter cube. If you have one, in fact, there are many times when that precipitation just starts, you will walk, boop, suddenly you will feel one raindrop on you. That's it. You won't get wet. That will give 37 dBc. Whereas this, you have an exponential distribution, and it has 9,000 raindrops, and then D0 of a drop median diameter of 1.3 millimeter. it will get only 7 millimeters per hour. And 7 millimeters an hour, you will get slightly wet. So that, you have to remember this carefully. This type of variability is what makes microphysics very challenging. It's not all connected to water directly in terms of volume. Okay. Next thing is, she's gone. She's the one who asked about shape of particles. And what I wanted to do is, I wanted to get, a lot of times you go look at raindrop, people bring pictures from overseas where they have observed in foreign labs. But I found out that there is a lab in India that actually makes this rain. So drops are not rigid body. And this mean shape is actually what you are measuring with the polarimetric radar. And I will show you. This is from IIT Hyderabad, Raindrop Research Facility. You can see how much effort it takes to generate a raindrop like it appears in nature, so that you can observe. It's not trivial. To repeat nature to make a raindrop and behave exactly the same way, it's not trivial. You can see the complex setup here. So this is available in YouTube. You can go and watch. So he sent me this, all this slide to me. Wow. Okay, I had a stereo. Yeah, there it is. So what people have done is they have looked at it from two. So there is also this type of oscillation, which is called longitudinal oscillation. That goes like this. And there is also a transverse oscillation that it will oscillate on the side. And a lot of times people misunderstood and call it as raindrop canting and so on. Okay, so come back all this. Finally, you take this to look at what is the shape of raindrop. Just like you did a raindrop size distribution, you needed to parameterize it and make it simpler so that you can understand this. So the best way to parameterize it is in the form of oblate spheroids that they form a flat base. If you go look at the GPM logo, the GPM logo is actually, if you go look at the symbol of GPM, it goes like this. It's actually a shape of a raindrop. And anyway, so the shape of a raindrop creates this, and then bigger drops. So Mother Nature gifted us this way. Bigger drops get more flat, and whereas smaller drops look more spherical. So this automatically enables us a way to measure the mean size of raindrop in a population. That's a God-given gift. Otherwise, there is a huge distribution. How do you measure the mean size? So that worked out. So people actually went around and then tried to measure shape of raindrops. So this is one of the earliest free measurement flying into storms with the aircraft. I had no idea what I was doing those days. I'm originally an electrical engineer. I was in an airplane flying that was getting bumped around, and all the food I ate didn't stay around. Then you ask some fundamental questions. I'm an electronics engineer. What am I doing in an airplane trying to measure raindrops? But the main point is, don't put boundaries on what you study. That's the main thing I was trying to say. You may never know what you're going to run into. So that has all resulted in eventually the whole development of dual polarization radar. Yes? Sorry, can you? Drizzle, you said?
Means rain when it is drizzling, means that time also the shape of the rain means raindrops is maintained like. That's the query,
drizzle, heavy rain, everywhere it has its shape.
Okay.
So drizzle, typically it's very small drops.
Yes, sir.
And it will be close to spherical. Yes. And when it's rain, it's bigger drops, and then it will become more like, what do you call, the idli shape.
Okay, sir.
Okay?
Okay.
Or in China, we call it dim sum shape. In US I call it as the M&M. It's a candy.
Okay.
It's got
Thank
the
you.
shape of that.
Thank you.
So there are a lot of people. All these are lab studies, and this is because those days there was a lot of controversy before we know this more. The shape there is different from the shape on the ground, and we don't know what's going on. So we actually took a plane and then fitted with optical probes and flew through rainfall. And then if it was published in 88, which means I probably wrote the paper in 86, those it takes a while to publish these papers. Okay. Now, then the next thing that's important in this whole microphysics of phenomena is fall behavior of this precipitation particles. So the fall behavior of precipitation particle, larger particles fall faster, smaller particles fall slower. So between higher level to lower level, this actually drives the precipitation process interaction. And all this you will see like in your face with dual polarization radar. So I'm trying to build a story here. So historically, there is a lot of studies that have been done to study them, to actually experimentally measure the fall behavior of particles. And some of these are here, and it's very simple. The olden days, it was hard. Nowadays, anybody who has a fancy disdrometer, you can actually do this yourself. And you can actually watch the downdrafts and updrafts and so on. Now let's bring radar into the picture. Until now, we have been just talking rainfall. So this is where the electrical engineering part of it comes, where essentially you have two polarizations, horizontal and vertical polarization. But those of you who are not deep electrical engineers, so you need coherent form of light. What's the difference between this light as opposed to, all this light is, randomly polarized. Sunlight is randomly polarized, all this cheap light. Whereas when you have laser type of light, that is coherent and it's polarized, and that's what makes it like the expensive source of light as opposed to cheap source of light. Essentially, but I'm just trying to oversimplify this. Don't take this to the T. So when you have horizontal polarization and vertical polarization, and also you should think in Mother Nature, everything that falls from the sky is on the average oriented horizontal vertical just because of pure gravity and then flow around the particles and so on. So as a result, even if there are things that you think it's oscillating like this, on the average it is horizontal vertical with respect to local Earth because of gravity. So that naturally gives a natural alignment to horizontal and vertical that makes horizontal and vertical polarization what is called as eigenpolarizations of propagation through precipitation, which is very different from the type of polarization that is used in military radars, where they use circular polarization. Okay, now I talked about variability at all scales. First of all, there is a size distribution. Then the amount of water changes, which means the whole distribution scales up and down. We have large number of water, and then you could still have an exponential distribution. You need to have a handle on these things. That is, keep the shape aspect separate from the intensity of rainfall. So some normalization concepts were introduced. That is, you normalize with respect to its median diameter, normalized with respect to some equivalent intercept that happens here. I'm trying to keep it simple. If you want to go get details, you go read in the book, so that you can get the inherent raindrop distribution structure. So this normalization process with this respect to the total water content and then median volume diameter tries to see, are there fundamentally different types of raindrop size distributions for different part of the environment, like West Bengal versus, I call it as Renigunta rain, you know, that's a hot region. And you just go look and, no, not Renigunda, Ramakundam. That's different. Okay, now let's go to dual polarization parameters in rain. So using the oblate spheroidal model, you can compute what is called as differential reflectivity. There's another challenge of understanding this properly because a lot of you have seen radar reflectivity. Radar reflectivity changes quite a bit and goes from 10 dB to 60 dB. And dB is a decadal scale. Going up by 10 dB means factor of 10. Going up by 20 dB is factor of, I want to see if people are paying attention. Yes, going up by 20 dB is factor of 100. So it's a 30 dB is factor of 1000. So there is a lot of variability in dB. So, and then, whereas you look at differential reflectivity, that differential reflectivity is different by 2 and 3 dB. People thought, how can I measure this 2-3 dB difference when things vary by 30 to 40 dB? It turns out it's fairly easy because horizontal and vertical polarization returns are very highly correlated. Because they are very highly correlated, you can measure them accurately. If they are not correlated, you cannot measure them. This is another mind-boggling question that people had a problem understanding this. Just because of this, it slowed down the progress of the field. That is, what is, again, this is not, I'm hoping, not the first course. For those of you who know radar reflectivity, what is the accuracy of radar reflectivity? And in terms of dB scale. Some of you in the back, students, what's the accuracy of, if you say you measure reflectivity of 40 dBz, how accurate do you think it is? You want to answer that? No? Who wants to answer that? Approximately. Somebody here? I think he wants to answer that. The person sitting behind Vaibhav. Yeah. You know the answer? 1 dB you said? Did you say 1 dB? Let's give him a hand. For 2 reasons. One is the answer is correct. Second thing is you're brave. Good. So it's 1 dB. So if one reflectivity is 1 dB and then another reflectivity is accuracy is 1 dB, you subtract that one from the other, the error should be 2 dB, right? And that's provided these two things are uncorrelated. If they're correlated, the variance of A minus B is variance of A plus variance of B minus 2 covariance of AB. And the covariance of AB, if the correlation is 1, the error is 0. So that's because of that. So that's where the difference between good radar and bad radar comes. If you buy radar, sometimes that's a piece of junk. It cannot measure the correlation properly. As a result, the accuracy of differential reflectivity will be all over the place. That doesn't mean that the weather has changed. It means the radar is cheap. Anyway, so this is how individual distribution parameters, when they increase in a, okay, then there is another parameter called a KDPE, which is differential propagation phase. I haven't defined this yet, so I'm going to back off from using too much of that, so we will stay there. Differential reflectivity is the difference between the reflectivity looking at it with horizontal polarization and vertical polarization. So essentially bringing in polarization essentially broke through the black box of microphysics of precipitation. Before, people had to fly aircraft, send balloons, and then telemeter data to even know where the melting layer is. everything, once the polarization radar came, it was like in your face. Immediately it's there. Okay, let's look at, everybody is talking about different radars at different frequencies. All administrators, they also know about the SC and X bands. That's where a lot of the weather radars are here. So differential reflectivity essentially gives an approximate measure of the drop median diameter. That is, what is the median diameter? Median diameter is like the mean. That is, half the volume of water is above the diameter, half the volume of water is below the diameter. To know that, it's a very strong piece of information. It is how the raindrop sizes are distributed remotely. You can just sit with the radar here and measure that. That in itself is, I think it's a very beautiful thing. I mean, it's impossible to, that's too much information almost, compared to all the unknowns and variabilities that happen in atmospheric precipitation. So at S band, you can see D0 and differential reflectivity, what is the relationship? Whereas if you go to C band, there is a little bit of wobbliness, and then X band, there is another variability and so on. But it's pretty much in the average you see in the big scheme of things, as the differential reflectivity goes up, drop median diameter goes up. Then also I wanted to show you some interesting way of plotting these things, which is individual particles. Previously I did this is distributional plot, whereas individual particles, why that wobbliness comes is because when you cross certain size, and this color, let me use the, this color is C band, and then this is, if you take individual particles, there is some difference behaviors in scattering, but when you put together a distribution, all that is tamed down. That's responsible for that type of wobbliness. Okay. So then what we wanted to see is, okay, all these days we have been busy looking at reflectivity. Now we have started looking at differential reflectivity. And so people have looked at it in the, what is called as a ZZDR plane. That is, when it, depending on where the data falls in the ZZDR plane, you can figure out what type of precipitation it is, okay? One is, if it's all here between 25 dBz, and then if it's a ZDR is 0, then it's all rain. And then 0 to 1, and if the reflectivity keeps increasing, then this is all stratiform rain. But if the reflectivity starts increasing quite a bit, it's convective rain. And then I have slides on this. There is a growth stage, and then if it goes very high reflectivity but no ZDR, it's hail. So these were some of the early days of starting to identify hydrometeors just in the ZZDR plane, which over time has turned into a very sophisticated field with almost like data science-ish issues. Okay, then I said the precipitation behavior is such that the correlation of backscatter between horizontal and vertical polarization is very close to unity. That is the magic of dual polarization weather radar. If it was not for that, it wouldn't have made such a big breakthrough. Somebody was asking me yesterday, yeah. That is the key, magic key, or the gift from God, that the scattering between two polarization is very highly correlated. Very high means what? It's like 0.98, which is what makes it possible. That's the key magic of the discovery of dual polarization. Then there is this differential propagation phase. You have spherical particles, let's say, and then behind that there is oblate rain particles, and then electromagnetic wave propagates. what happens is when it goes through spherical particles, the horizontal and vertical polarization, their phase delay stays the same at both polarizations, whereas the phase delay is larger. Why don't you come closer? You're struggling with camera very far. Come closer. Come to the front. If you had come earlier, I wouldn't have even let you sit there. See, the reason why that back is empty was we forced everybody to come forward. So it's not an accident. You let people to sit by themselves. Most of the people like to sit in the back so that when they watch cell phones, nobody would know. Anyway, whereas when you go through rain particles, the delay in phase is different, which makes the differential phase steadily increase due to propagation. And I used to tell a story, and let me see if I can tell it clearly here. What is important to this differential PDP, KDP, Subrata was telling me it's a tough concept. And let me see. How many of you are listening to this for the first time? KDP, PDP. Raise your hand boldly. Good. Let's try to make you understand this. This is my own story, okay? I'm not repeating somebody else's story. Imagine this is a big ballroom where people are standing, okay? It's not a lecture room. You know what a ballroom is? Yes, no? It's just an open room, okay? A lot of us are standing there holding some, hopefully, orange juice, not drinks. And then I have to walk from this end of the room to that end of the room. I am velocity of light. I have a specific speed. I will just walk to the end of the room. If one person is only there in the room, I walk from here to there. My speed doesn't change. So one of the things radars are very good at, or electronics, is measurement of time. They can measure time at nanosecond time scale extremely good. So now I start populating this room to, let's say, 2 persons every square meter, like that. More people are standing. Now if I have to go from this end of the room to that end of the room, I have to dodge people like this and walk around. My speed to go from here to there will get slowed down, okay? I put more people in this room and distribute them uniformly. I will further get slowed down, okay? Then put more people. I'll further get slowed down. Now I am thinking very cleverly. You know what? I know my speed. Just measuring my speed, I'm going to guess the number density of people in this room. Right? If there is a one-to-one connection between the number of people in this room and my speed, that is exactly what is happening in KDP. What KDP is looking at is the amount of change of phase, which is slowing down, is proportional to the number density of raindrops. Guess what? The number density of raindrops or the volume of water is what I need to measure. Turned it around and made it into a very clever measurement. This, I am going to even make it more clever by bringing polarization. I'll show you how. Allow people to randomly stand in this room, and then you have a pointer. You have a pointer stick. No, I need not an electronic pointer, like a stick. Okay. Okay, then you have to imagine this. I have to hold a stick in my hand like this vertically and walk across the room. Okay? I will walk very easily. Next time you tell me to hold the stick horizontally and walk, I will get slowed down quite a bit because I have to dodge around people. I'm holding a horizontal stick. Same thing is happening at 2 polarizations, vertical polarization and horizontal polarization. The speed changes depending on which way you are holding the stick. Because any differential measurement in electronics is very accurate. So that's the secret sauce of differential propagation phase and why it's so successful in measuring rainfall accurately. Got it? That's the basic physics. Rest is all mumbo jumbo, electronics and so on. So what is happening is, so KDP is directly proportional to d to the 4, and so it is used to measure without all this calibration of radar, all those issues, volume of water. So that's one of the reasons expand radars have become very popular. Okay, now let's take all this together and bring it to, I'm going to call it Goswami style, and build the whole precipitation physics story into this. And I'm going to point location by location, talk about the precipitation process, and then how you are measuring it with dual polarization radar. This is a big storm over northeast. Let's make it a Kal Baishakhi storm. Big storm, okay? How many of you know Kal Baishakhi storms? Oh, good. Many people have. That's a destructive storm, right? So you can see this is -20, -40, because Kal Baishakhi storms are really tall. And I don't know if I've shared this history with you. Some time ago, we did a major experiment in Argentina called the Relampago. And one of the reasons we went there is because observing from space, that La Plata basin region is supposed to have the tallest thunderstorms in the world. But nobody knows why. So we wanted to go study that. So we took our radar and everything. According to what I have heard, the second tallest storms in the world are these Kal Baishakhi storms. So there's another thing. We need to have a national experiment to study Kal Baishakhi storms and understand them thoroughly, the microphysics. I have a big list coming to you. Anyway, so let's say this is, because you see it's -20 is probably around 10 to 12 kilometers, and -40 is about probably 15, 16 kilometers, and you know these storms will hit the tropopause. And, and then you have differential reflectivity. Both of them are increasing, reflectivity and differential reflectivity. That is updraft. And then with the updraft, there is fragmentation and splintering. And then, which means reflectivity will go up, ZDR will come down. And in here, aggregation. That is, ice crystals cling with each other and then come down. Reflectivity will go up, dual polarization will come down. Melting, reflectivity goes down, differential reflectivity also goes down here. And then collision, coalescence, and breakup. This is ZZDR. And then ZZDR going up here due to growth. And then this is evaporation in the base of the storm. That is, what do I call, Ramagundam storms, where it's very dry below, where reflectivity goes down, but the ZDR with vertical remains steady. So by watching this vertical profile of these dual polarization parameters, you can pretty much give the prescription on what type of microphysical process is going on. So I wanted to show you in this context a video
of
on
the water molecules. As these droplets grow, they become heavier and start to fall through the air.
the smaller
Smaller drops will get evaporated.
evaporated.
But sir, that phenomena is there in the central part of India also during
Oh yeah,
the...
it's there in many parts of India where where it's dry. Like for example, Indur.
Even for the Hindupur, Anantapur districts,
you can, no, you
the
didn't-
Rayalaseema.
You can even go further. You
Yeah,
can
and even
go
the
to
north also. So
Indore. Take
Huh.
Indore. Let's make it
Indore,
rain.
yeah, Indore. There also it is the same
Yes,
thing.
yes.
So when you said Ramagundam specifically,
No,
this
it's just
it's just an example.
Ramagundam, and people understand that.
Yeah, because the northern part or the central part of India
Yes.
also faces a
Yes.
similar kind of
Yes.
heat and temperature. So at that time also the same
Yes.
phenomena happens.
Yes.
Even in the northwest India also same phenomena happens
Yes,
during
yes,
the
yes.
pressure gradient type of convective activity.
Denver, Colorado is very known for that.
Okay, so it is the same thing.
If I kept using Denver, many people will connect. So these are regions where they create what is called as dry microbursts Okay. So there is a downdraft, and then you won't see precipitation, but then there is
Yes, yes, sir.
downdraft.
This is one of the phenomena that happens most dominating during the March to April. That is the
Yes.
pre-monsoon period in
Yep.
India and very of the hotter places. So the same effect which you are trying to say as a
But the main thing is, my main point is you can observe it with the radar.
Okay.
And determine that is the cause.
Okay. Thank you, sir.
In a large scale. Yeah.
Thank you so much.
You can ask a question so long she agrees. Yeah, she says one more question. She's the boss.
So, just like you showed that Z and R, I mean, the Z can be same, but R can be different, right? Depending upon the size of the raindrop. So, in the KDP example that you used, the speed of the light can vary, even if your number density is low, but the size of your raindrops is large. So, how do you differentiate that in your dual polarization KDP or phi thing?
So it's basically proportional to the volume of water.
Yes.
So if the volume of water is made up of a lot of little drops as opposed to a few big drops, the phase change will be the same. Okay? So the way you think about the example I gave is a lot of little kids that are standing. You can go through them easily, but there are some big fat people, it will be harder for you. It takes only a few people like that. So it's the volume of water that's important here. It's not the number of drops. It's the combination of number times size, which makes the volume. Okay?
Thank you so much, sir, for your insightful deliberations. As we are running out of time and getting delayed with like 45 minutes or so, so we'll be breaking for lunch now, and we'll be back in the hall within 30 minutes to start with the next session. And there's a small announcement here again. We have a travel desk opened up outside the hall. So anyone who is interested for traveling and exploring in and around Guwahati, you can inquire at the travel desk. Thank you so much.
Sorry?
So your next PPT is...
It's all here. Well, I have to continue. close that door. And yeah. So what you will find is with height, reflectivity will decrease, but ZDR will be almost constant. And I wanted to show you some, and it's very, very common in complex terrain. So what you're seeing here is data from California and Northern California here actually. So we had NPOL, which is NASA dual polarization radar. So this side is ocean, this side is mountains. So the radar, instead of doing PPI volume, you cannot see any microphysics doing that thing. That's a dumb way to scan. So what we do is we just do over the head scans like this. So simultaneously you can look over the ocean and then you can look over the mountain complex terrain. So this is the reason you see, this is Pacific Ocean. This is Bay Area. We are looking up into the mountains, and this is the scan, okay? And at that time, it's this is the 0 degree isotherm. That's the bright band. This is into the ocean region. So moisture is coming this way. And then co-located with this was D3R radar, which is KU and KA band, which is higher frequency. And you can see this is mountains, that terrain you see. So as you get close to the mountains, you can see reflectivity is increasing. And this is KDP in the ice region aloft. And KDP is positive. That corresponds to oriented ice crystals because of what is called as Bergeron process. And then the increase in reflectivity below the melting layer is because of collision coalescence, which is basically what I called in the theoretical model here. You can see due to collision coalescence, reflectivity steadily increases as you get close to the ground. Whereas the differential reflectivity will be nearly somewhat steady below the melting layer. And as you get close to the mountains, the reflectivity will increase quite a bit, which means actually the rainfall, as you get closer and closer to the mountains, is increasing. And it's not illusion. And the problem is, a lot of times as you get close to the mountain, not only the rainfall increases, and because of the complex terrain, the water cannot just stand there, it will come down raging. So that's why you get all these mountain flash floods. And this is the type of phenomena, things that creates things like Uttarakhand floods and all that stuff. So and you see here the reflectivity is of the order of 30 dB, and as you go here it goes to 45. It's 15 dB, 20 dB more, which means what? It's a factor of 100 almost increase in water. So that's a lot of water as you go close to the mountains. And this will also be hard to observe because the radars have to be clean, because it will be otherwise contaminated by ground clutter. And a lot of people will ignore this increase in reflectivity as contamination by ground clutter. So this is real. And so we have researched this quite a bit. And I have talked about this as the rainfall increasing very high. Then here comes the evaporation problem, which is the opposite. And here you see, these are all theoretical models, so it's not a good thing to go study after lunch. But I will talk about what it does to the raindrop size distribution. So typically what you will find is with height, the differential reflectivity will be steady because of evaporation, but the reflectivity will fall rapidly, which is exactly the reverse of what happens due to collision coalescence. This is the dry environment due to evaporation. So here is an example of X-band RHI observation. you can see the reflectivity is fairly high, and then as you get close to the ground, almost everything evaporates. And then again, you can see this well only when you do this vertical RHI scans. If you do PPI scans, you have to kind of imagine in your mind and then build all this evaporation. Whereas differential reflectivity, you see, it's almost steady. So this is all microphysics 101. That is being studied all the time, but you can just see it very clearly with your radar. Okay, this is, I had a nice slide, cartoon, but it's playing here, but it's not playing here. Huh? You have to change screen. So you can see the bigger drops fall faster. So this creates what is called as a sedimentation problem. So as a result, big drops cluster below and small drops are above. That not only in vertical movement, also in horizontal movement sometimes, and that creates its own ZDR issue. So what you will find is, I just put impact of sedimentation and radar observation. You will find in the initial phase, the rain shaft, we may just observe few sporadic raindrops as it's coming down with large differential reflectivity and very moderate reflectivity and very low rainfall rate. But when rain reaches a mature stationary state, differential reflectivity will decrease, whereas the reflectivity and rainfall rate will increase. Okay, so that's the initial sporadic stage. Only few raindrops are coming. Come to the front. Because first back you'll sit, and then slowly you will lean, and then next you'll. So initially it will be like this, sporadic drops. Later it will become like this. This is modeling of this. Okay. So then if you have a tornado style vortex, so this is reflectivity, and you can see there is a hook echo. This is high reflectivity, size sorting from wind shear. with a supercell tornado. And you can see these reflectivities are 55, and then you can see the hook echo. Have you heard of hook echoes and tornadoes? Yes? Now people are starting to observe tornadoes here also, right? Where did you get the last tornado here? In Bengal somewhere I thought there was tornado. Punjab? Last big tornado I heard was in Bengal somewhere. Yeah. Alipur. Yeah. And I think, in my opinion, tornadoes have been there even before, but we are starting to look more carefully with, because on ground, unless you really, you'll see a lot of only damages, and you don't know if the damage is because of straight line wind or tornadic winds. But if you're a little far away and if you're in a dry environment, you can really see the vortex visually. But you see in the Doppler velocity, the tornado very beautifully. Positive velocity is going away from the radar, negative velocity is coming towards the radar, and you can see the tight vortex here. So here it's blowing away and it's coming in. This is in the horizontal plane. But in the vertical plane, and when you see the differential reflectivity, it will be very positive on this side of the arc, whereas not in this side. Why is it that way? Because it's not a horizontal phenomena, actually it's a vertical phenomena, and I will explain that. This is what is happening in the vertical in a tornado. There is this weak echo region where things get sucked up, but here, because there is updraft, only the big raindrops that fall faster is able to fight against the updraft and then able to come down. All the small drops will get blown away. So as a result, you selectively have only big drops, which means you have excessively large ZDR compared to the normal reflectivity. Whereas on the other side, it won't be like this because of this blowing wind. What is the mental model for this? Is this. Because of this large velocity, the small drops will get sucked in like this, whereas the big drops will fall fast, and then you see very large ZDR here. That's happening here. So when you do a ZZDR scattergram in those regions, it will look all awkward and it will be out of the normal population. Whereas reflectivity, differential reflectivity from a normal steady rainfall will be something like this. That's the big difference. So to summarize, microphysical process. There are 4 types of microphysical process: evaporation, size sorting, coalescence, breakup, drop breakup. There are different vertical signatures of ZZDR. Okay? When you have evaporation, reflectivity will drop significantly, whereas size sorting, the ZH ZDR will go in this opposite directions. And then collision coalescence, both are increasing with height. I mean, this is the complex terrain issue, and then this is drop breakup. Okay, now I am at a fork in the road. Either I could talk about ice process, or I could talk more about rainfall. What is your choice? Previous slide. Yes, sorry, y-axis is altitude, yes. X-axis is the value. Yeah. There is the collision coalescence and then evaporation. So that's the collision coalescence is the main thing that I wanted to bring attention to in complex terrain. Okay. So, you know, we could go ice crystal microphysics. We see a lot of signatures, but I don't know if that's of interest or you want me to move to the rainfall story. As advertised, this talk was supposed to be about rainfall. So I just completed that stuff, but I'm going to skip ice microphysics because I assumed you don't care about ice microphysics that much. You care? So let's take vote. Who wants to hear more about rainfall estimation problem? Raise your hand. Raise well, I cannot see you. Okay, ice microphysics. Sorry, that's minority. Maybe I'll selectively show a few things. Let me skip all this. I'm going to change. Oh, I lost my file. Can you get back to the main screen? Yep, this one. Okay. This is a very difficult problem, rainfall measurement. And it has been challenging, like I said, right, for a long time. People have been estimating rainfall using radar, but you can't complain because you have to do something. So instead of having no measurement, making an erroneous measurement is just okay, so long you know the level of error. There's a typo here. Okay. Radar equation for volume targets. That's one thing you have to fundamentally understand. That is precipitation and radar, as opposed to looking at radar seeing airplanes. Radar seeing airplane is called a hard target or point target, whereas when it looks at precipitation, it's called as a volume target because these particles are filling the volume. And then, so the way it is quantified is, until recently when you get backscatter from radars, it is all just getting signal. Whereas this is getting quantitative. This is not trying to figure out whether it's high, low, like that. It is how much. It is like talking about volume of water. So the received signal is determined by hydrometeors in the resolution volume, and it's going like this, and you are actually counting the amount of raindrops and water with these equations. So what you do is, let me skip this, these are a little intense for post-lunch lecture. Essentially, you get the reflectivity is proportional to the lambda to the 4 divided by pi to the 5 k square n of d sigma d. Whereas this z, which is this is the ZE, equivalent reflectivity factor. Z is n of d to the 6, because this and this can be related, because the sigma, which is the backscatter cross section of a raindrop, is written as pi to the 5 d to the 6 divided by lambda to the 4. So what it means is, look at this sigma, which is the backscatter cross section. D to the 6 is reflectivity factor. Once you have fixed the size of a particle, d to the 6 is fixed. But if you see it with higher frequency radars, to the radar they appear bigger, because sigma is the backscatter cross section. Backscatter cross section is a bigger, it's got actually units of, anybody knows what's the unit of sigma? I was going to tell you, but sorry? I thought somebody is mumbling the answer. Can you speak up?
Sir, it's backscatter cross section. Cross section has an area of meter square.
Meter square?
Yes.
Is that what you said?
Yes, sir.
Yeah, it is meter square. Okay. And whereas this is d to the 6, which is meter to the 6, and this is lambda to the 4, which is meter to the 4. You can see the units cancel. And what I'm trying to say is, that's the reason when you want to put radars in space, you go to higher frequencies, because the same particle looks bigger, and the amount of signal that's returned is actually directly proportional to sigma. It's basic law of physics. Now, long time ago, there used to be a myth that C-band radars don't work in Indian conditions. I'm not joking. I've had to deal with this myth coming to IMD. And IMD was told that only S-band radars work, C-band radars don't work here, because you lose the signal. So lambda to the 4 is that factor of how much stronger the signal is. What is any IMD person here? S-band wavelength, do you know how much? Approximately 10 centimeter. C-band wavelength, approximately 5 centimeter. 10 to 5, factor of 2. So if you see lambda to the 4 factor, one is 10 centimeter, another one is 5 centimeter. You have right there in sigma 2 to the 4 advantage. So you get quite a bit of advantage, extra signal, before you lose things for attenuation. I don't know where this came from. This is called as vendor-induced physics. Anyway, that doesn't matter now, but eventually there are a lot of C-band radars now. There was a time that people believed C-band radars don't work in India. And so that was a different time. So rainfall rate, by definition, is the flux of water coming through an area. And when you define it in terms of flux, it becomes some constant multiplied by d to the 3.67 n of d dd. Okay? So Z and R are different moments of the drop size distribution. Okay? And here you have 5,000 drops, all 1 millimeter drops, and this is 1 meter cube. This is 1 meter by 1 meter by 1 meter. This is like a bathtub or like a laundry tub or something. And water storage in the old days, you've seen 1 meter by 1 meter by 1 meter. And it's got 35.6 millimeter per hour. Whereas the same reflectivity of 37 dBz, if you had filled with 2 millimeter drops, you get only 6.7 millimeter per hour. They will both give you same reflectivity. So you cannot have directly a ZR equation. If you have a fixed ZR equation, going from Z to R, it will give the same answer. I have just shown you the same Z produces two different rainfall. That's the reason for not dealing with ZR equations. But look, at the end of the day, we still have to do something. IMD cannot say, I don't have an equation. The user will ask, give me some rainfall. It's better to put some rainfall than sitting and saying, I don't know how to do it, or it's not raining when that person is getting rained on. So for practical reasons, though people make fun of ZR equation, you have to do something. So that's why you do that. So the same case, 1 4 millimeter drop, and then you make an exponential DSD. They both have 37 dBz. But in one case, it's 1.2 millimeter per hour, whereas the other case, it's 7.4 millimeter per hour. This is the fundamental rainfall estimation problem coming with radars. So everybody refers to Marshall-Palmer distribution, and many times when somebody gives you a rainfall rate, and if they don't know what ZR equation they used, there is a 90% chance they used Marshall-Palmer relation and they didn't know it. That's all. I don't know, I used a relation that it was already programmed into the code. And then you go look what it was Marshall-Palmer relation. Because no matter what you put, you will ask why you put it. Might as well put something that everybody has been putting it. So Marshall-Palmer relation was because they measured the raindrop size distribution in Canada, outside Montreal, and they put that equation, and then it's been sitting there since then. Okay, here are some example NextRad ZR equations. This is rainfall rate, this is reflectivity, this is cool season, this summer deep convection, and Marshall-Palmer. If you plot Z versus R, you get 3 different curves. And this type of thing is more for what IMD. And then again, Z versus R, summer deep convection, cool season. See here, R is on the y-axis, Z is on the x-axis. Here, Z is on the y-axis, and R is on the... Okay. Here is a conceptual way of proving why you need dual polarization. Okay? You take all the distributions, and then this is Z versus R, and then you make one big line fit to all the data. You get this formula. Z is 250 R to the 1.63. When you get raindrop size distribution data, you can just put all this and you will get some result. Doesn't matter what data you have. You have disdrometer, you collect data, you do a fit, you will get an answer. And then you say, this is my ZR equation. This is what IMD can do if they want, okay? But you can see the main reason is Z is 6th moment and R is 3rd moment, and this is the reason you need dual polarization. So in order to do this, why did we study microphysics? Because originally it was fun because you could understand the microphysical process. But that doesn't bring revenue. You can write papers, you can be a scientist. That's people will say, yeah, you wrote your paper, and then what happens next? Whereas we want to convert this, I have already gone through this, so I'm going to skip this. So what we want to do is, we wanted to convert this to rainfall, and then we get the dual polarization parameters. So this part of it I didn't show you before. The scattering matrix of any scatterer is written as SHH, SHV, SVV, SHV, SVH. And for a sphere, this is written in this form. And the relation with cross section is sigma is 4 pi s square. These are all basic description of scattering. So there are so many dual polarization radars. But when the type of dual polarization radar you are using is one of this many kind, this is alternate transmit, simultaneous receive. That is, you transmit once at one polarization and then you receive H and V, which means one will be a copolar signal, another one will be cross-polar signal. Then you transmit the other polarization. That's actually the most pure form of making dual polarization measurements. That's how the measurements started before. But then what happened later is all this switching and everything, that high power switch was very hard to maintain, and it became expensive. Whereas it was simpler to split the power and transmit at both polarizations and receive at both polarization. That's called simultaneous transmit, simultaneous receive. That is, you have one transmitter, dual receivers. So if you do that, I have only 28 minutes. In the interest of time, I'm going to skip some of these slides. Yeah.
Should be receiving at both the receivers for the simultaneous transmit, simultaneous receive. Both the receivers will be programmed in the sense designed to receive at slightly different frequency or something like that.
No, they're all at same frequency, and so that's what happens is you transmit. You hope. This is a good question. I was trying to gloss over something. Imagine you didn't have rain, and the target that was sitting there was a angled wire like this. So what will happen is you transmit horizontal and vertical. You are hoping the target doesn't change the polarization. That is, there is no cross-polar signal. And any target that is axisymmetric, they won't create cross-pole. So raindrops and ice crystals, historically, they don't create cross-polar signal. Their LDR, which is depolarization ratio, it's about 20 to 30 dB down. So it's as if you sent in a river, you sent red color water and blue color water, and without mixing, it just landed up on the other side almost the same way. So when you transmit horizontal polarization, what happens is horizontal polarization gets transmitted, a small portion of it becomes vertical, you just ignore it and look the other side, and you assume the same thing goes. Similarly, you transmit vertical, a small portion of it becomes horizontal and leaves the antenna because the antenna is not perfect. But then you ignore that and you assume vertical is coming, and then you receive the two things, and then just go on. In order to use different frequencies, you have to transmit also at different frequencies. The problem in doing that is you kill the correlation between the two polarizations. that makes the measurement more difficult. I'm going to skip all this. Okay. Differential reflectivity is a relative measurement, and it's more related to the particle size as opposed to the strength of the rain. So the strength of the rain actually gets cancelled. And then I showed this before, which is the relation between differential reflectivity and the median volume diameter at different frequencies. So this is used to invert rainfall. Okay, here comes the main story. What you do is, you have disdrometer data, okay? You take all the data and then you just bunch raindrops that are between 1.2 and 1.3 millimeters and plot them. Plot reflectivity versus rainfall. And this is all data. This is not just made up. All that scatter plot will fall like this. You bunch data between 0.7 and 0.8 millimeter, they will all fall like this. You bunch the data from 2 to 2.2 millimeters, all the data will fall here. But you see, they all have a common slope, but they keep moving this way. This is data from iFloods campaign. iFloods is a NASA experiment. It was done in 2013. This is all from data. It's not conceptual theory. But you put all the data together, you will get one big solid line, which is Z is 250 R to the 1.63. Okay? How is that happening? That line is running across like this. Whereas if you just took only this data, there should be one ZR equation here. If you took only this data, there should be another ZR equation here. If you took another data, there should be another ZR equation here. So that's what happens when people go do experiments. They collect data in some region and they come with one ZR equation depending upon what all data that got into the ZR equation computation. That's why a lot of people have tried to say this is the ZR equation for Delhi, that's the ZR equation for Jaipur, and that just keeps varying all the time. So it's like a non-winning game. It is like, it's as hard as New Year comes and we all have to exercise and lose weight. It's like that. You keep on going, you do this, you do that, but nothing happens. You can never get the rainfall properly because you're fighting against Mother Nature. In reality, you have 3 different ZR equations with these 3 different setups. Now you see the basics of the problem, especially all the people in IMD, application people with the ZRs. Because what happens is, depending on the type of data you took, if it's a summer convective rainfall, then that day, whatever you took, it happened to have a lot of small drops. And then, because it was raining heavily, there was no evaporation, you got one ZR equation. Another time, the humidity was low, then it had a lot of big drops, and then ZR equation is different, and so on. Or you go into a dry region, ZR equation is different. So, if you plot, this is a supercell storm, this is horizontal reflectivity, this is a vertical reflectivity. This was measured by Sioux Falls NextRad at 0.8 degree elevation. It's just some NextRad data. Okay? So, this is horizontal reflectivity again, and this is differential reflectivity. You see, the reflectivity refers to physically raindrop concentration and size, whereas the differential reflectivity is proportional to the mean diameter. So all these regions have mean diameter very high, whereas this region is a combination of concentration and the diameter. It gives completely independent information. It's the same data. I am sure in Delhi radar you're used to seeing stuff like this. So then the next thing is PDP, which is due to propagation of electromagnetic waves. And the propagation phase is the phase shift between horizontally and vertically polarized wave. And this is completely a phase measurement. Is Subrata here? He's missing. So he asked me during breakfast about PDP and KDP. So that's difference between AM and FM radio. I don't know how many of you, well, only time you are listening to radio these days is maybe while you're driving car. Even maybe that time you listen to some internet channel. Anybody listens to radio anymore? You do. Well, that also while driving, right? Or no? At home? Wow. Okay. Nowadays the only people who listen to, so the main difference is, if you knew what the radio problem is, AM radio is a little noisy, whereas FM radio is a little clean. I thought there is some, every time I watch movie they talk about some Mirchi channel and all that stuff. Nobody listens to all that. Anyway. So the reason is because everything is dependent upon phase. You've seen this before. And another important thing is KDP scales with frequency. So for the same amount of rain, you get a lot more differential phase as you go up in frequency. That's one advantage of going to higher frequency radars. And another advantage is this is C-band and that's X-band. X-band radars are more compact. Okay, rainfall relation. Now you can use ZDR and ZH to get a RZZDR. Okay, so what you can do is you can see this is for this data set. You can get a RZZDR relation, and then if you want, you can fine tune this with rain gauges, because still hydrologists believe everything the rain gauge says more than the radar says. But that's a different discussion. I'll come, if I have time in the end, I will come back to it. So essentially what happens is, I'm looking at the clock here. So there are three types of rainfall, common rainfall relations that you can get. This is the traditional ZR equation. And then this is ZZDR. And this is KDP. But finally what you do is you get a Kichari out of everything. So if you just go compute RZZDR, you do this at S band. This is the equation you get. C, Z to the B, ZDR to the A. These are the various coefficients you can get. And this is all available in the book, so you don't have to take notes. Now, you do these three things, and then R is C, ZH to the B, ZDR to the A. So what you can do is R is C, ZDR to the A, you can combine, and then ZH to the B. The ZDR is based on diameter, so this basically becomes a ZR equation, where this thing changes with ZDR. This multiplicative factor, depending on the type of rainfall you encounter. That's one way to think about it. So you do this, there is a lot of what do you call error propagation issues, and what is the accuracy of these rainfall relations? So if your variability is really determined only by microphysics, there is no measurement problem at all. Then this is the error due to ZR relation. This is the error due to ZR rainfall versus rainfall computed by ZZDR. Of course, this is more accurate because you are using two parameters. But that's only due to parameterization error only. We are not talking, you are bringing two measurements, which means you get twice the opportunity to make mistakes. So you have to account for that. So and then you account for measurement error, then these things start looking comparable. This is still more accurate, but the propagation of measurement error reduces the advantage of using two measurements. It's not like a slam dunk like before. So the same thing is true with KDP ZDR. This is parametration error with measurement error. This is RKDP. This is RKDP ZDR. This is more accurate by using two measurements, but at the low end, it's still got errors. Okay, let's skip this. Let's get into, as you get into higher frequency radar, you need to do attenuation correction, okay, to even use Z. What are the principles of attenuation correction? Propagation effect. We implicitly assume that the atmosphere between the radar and the target does not affect the transmission, but to measure rain, you need to go through rain. There is also attenuation from gases and water vapor, but these are really negligible, and they can be figured out once you fix the frequency of the radar. And then the precipitation affects weather radar measurements based on the received power. So in order to understand this, here tells you the extinction cross-section. That is, the backscatter signal is coming from backscatter cross-section, whereas attenuation is described by extinction cross-section. There is a plot of extinction cross-section versus diameter, but that extinction cross-section also is a function of temperature. Very cold rain attenuates a lot more than warm rain. So here is attenuation as a function of frequency, and as you can see, for different rainfall rates, it increases with rainfall rate, it also increases with frequency. Higher frequency radars have more attenuation. That's one of the reasons historically we used to have only S-band radars, because we didn't know how to deal with attenuation. Because if you have weak signal, you don't know if it's because the storm is weak or the storm is strong and then it suffered some attenuation, and then the final received signal you get is weak. You don't know the difference between the two situations because we didn't know how to handle with attenuation before. That's the reason why old days we had only S-band radars. Is that part clear? That's the origin of S-band. Because S-band, naturally, attenuation is negligible. Frequency S-band, 3 gigahertz. It is so small. Attenuation dB per kilometer, let's say at even 100 millimeters per hour, 3 gigahertz, it's 0.1 dB per kilometer. Whereas if you go to X-band, which is 10 gigahertz, to get the same, you get the same amount of attenuation at 1 millimeter per hour, what you get at 100 millimeter and S-band. And if you go to 100 millimeter here, you get 10 to the 1 is 10. It's about 5 dB per kilometer. You don't have enough power in the transmitter for building a long-range radar. That's the reason why there is no reason to build 100-kilometer radar. I've seen many bids from government asking for X-band to operate at 100 kilometers. It's cheaper to put 2 different radars and cover the 100 kilometers as 50 and 50 than to build 100, because you need to put out enormous amount of power to account for attenuation. I wish somebody would tell this to, because IMD, many organizations just send out X-band radar bid for 100 kilometers. It's not needed. That's why the X-band radar network concept came for X-band. So the effect on reflectivity, you can see the same rainfall. This is S-band observation. See how much attenuation is there. This is C-band observation, same precipitation. Obviously, this is a long cell. That is, the storm itself is 70 kilometers long. And if you look through that storm, that's very intense storm, you get a lot of attenuation. And how do you correct for attenuation? You can correct for attenuation using KDP. That is the main game changer with dual polarization. So this is S-band, C-band, X-band, KU band. What is the attenuation correction coefficients? Okay. So these are different formulas that are available, and I'm going to skip this. So what I wanted to show you is some interesting examples. So this is reflectivity radar. This is radar in Italy. I wanted to choose and get radar data from somewhere else instead of showing all the time my radar. This is reflectivity. This is differential reflectivity factor. And this is differential propagation phase. You know, phase goes only 0 to 360 degrees. After that, it folds. So differential propagation phase, you have to unfold them. This is PDP unfolded. And this is KDP, which is specific differential propagation phase. This is some data from this date. Now, we get 9 hours of accumulated rainfall on this storm with this radar, rainfall accumulation. Now, this is done using ZR equation, and this is done using RKDP. And there is quite, it shows a pattern. It shows high rainfall here, but this rainfall is about 100 millimeters here, and this is showing 250 millimeters. It's like a factor of 3 difference. Going from 100 to 350 millimeters is flood versus no flood situation. So this is ZH, this is KDP, and this is comparison with gauges in this case. And you can see the gauge is much closer, I mean the KDP is much closer to 1-to-1 line. So if you used a simple ZR equation in this case, it didn't work out. Now, this is the radar, and this is where, and then the beam, if you, depending on where you make the measurement, okay, because the radar sometimes, you know, main thing is that I'm talking about complex terrain, you get elevation angle of minus 0.3 degree, which is here, and even though there is partial beam blockage, it actually measures fairly good rainfall with KDP. So this is the same rainfall measured with 0.3 degree elevation. And this is measured with 1 degree elevation, which has no blockage. Now, there is an upside and downside. You want to make measurement very close to the ground so that you remember due to microphysics, I talked about vertical profile of reflectivity. So you want to measure very close to the ground so you get to capture the rainfall to the ground. But then if you measure very close to the ground in complex terrain, you are affected by all the terrain features like mountains. But then you, as a compromise, you can go to higher elevation. But if you go to higher elevation, then you are not making measurement close to the ground, and that's what this is showing. this correlation with the gauge rainfall here, it's less than the story I showed before, where it was much higher, the correlation with gauge. Okay? Let me skip this, and then I have okay. There are typically rainfall algorithms, or what they are used is blended algorithms. This is observed reflectivity, and this is attenuation corrected reflectivity, and this is KDP, and this is PDP. And you can see attenuation corrected reflectivity is much better than regular reflectivity. Now I want to talk about QPE methods. Rainfall is done by using some sort of a blended algorithm because you want to take the advantage of all procedures. So this is what is called as the so-called drops algorithm. Typically blended algorithm scheme, this is for S-band radars. What you do, so you do hydrometeor classification first. Based on that, you come up with an algorithm, and this algorithm in the literature is typically standard, and it's called drops 1.0. And then there is a similar drops 2.0 also. This is for S-band radar. Now here is a solution for C and X-band radar, where attenuation and differential attenuation is more intense. So here how the blending algorithm happens with rainfall estimation problem. So here is a C-band radar, and then the left-hand side is RZH versus R. This is a pure ZR equation. This is RKDP, and then this is blended ZH and KDP. And you can see these two things agree better compared to that. So this is same thing, but you get cumulative rainfall. It's more of that same stuff. I want to give time for, some of this stuff actually I will talk in my opening talk tomorrow, so I'm going to skip this. This is the AQPI example. So main thing is, when you are in complex terrain, it's best to do vertical profile correction if you are using reflectivity anywhere in your rainfall estimation. That's the basic final recommendation. If you are not doing vertical profile correction, it is making mistakes. That's the main story here. Because here is, you can see without vertical profile correction, it's a very busy slide. The comparison with gauges has a lot of biases, whereas when you do vertical profile correction, a lot of the biases go away. Okay, there's a composite diagram. This is, if you do it only over X-band radar domain, then you get a much better example. What I'm going to do is, okay, here is the final finale. So what you can do is, you can actually, I've not gone into details. You can get different type of rainfall, trying to figure out if it's a bright band rain or non-bright band rain, because bright band rain is stratiform, non-bright band is convective, and then you can do that. And then you can get a composite and then do a ZR equation, and then you do dual polarization, you get the best rainfall. That's the bottom line in AQPI. That's the end, and exactly on time. Time management. Do we allow them questions or we have to go to next speaker? 2 minutes. It's at 25. Yes. Who goes first? Okay, go.
Because it is rotating from, so if you go to the uncorrected 5 degree, can you go to
I mean unfolded.
unfolded? Yeah.
Okay.
So how do you start the removing the effect of folding?
So typically what you do is at the beginning, okay, the way it's done is you, in almost very light rain or something, you get the system FDP. You actually have to measure that. And then make that at, that's because FDP is like a fixed shift. So make it, it depends on how your display is going, minus 180 to 180 or 0 to 360. Let's call it as 0 to 360. Start that at around 5 degrees or something. Make the system phase shift 5 degrees, and then you keep on increasing. Then again and again when you measure even in clear air, the system FDP will be around 5 degrees. Then you can take care of that. Instead, if you let the system FDP to be what it is, then it will immediately start at a high level and then start jumping. So that's what we do to take care of that FDP correction.
So it may be a silly question. So these all radars are bigger radars. So I would call them elephant. But let's see, I want to get information for some particular event. I want to take my radar into within system, like a few kilometers measurement. I want to have very high resolution. Can we, is it advisable to build radar based on, these are pulse radar on FMCW technique?
Well, there are radars you can build out of FMCW technique, but there are also pulse radars. You can get it to close range. It doesn't have to be FMCW only.
Okay.
And there are small pulse radars that we call them deployable radars.
Okay.
That is, you go and wait and get high resolution data. Most of the X-band that I am talking about, they're all meant for 30 kilometers range maximum. Not the IMD style 100 kilometer X-band radars.
30 kilometers radar also, it's like you cannot take it to the, like at
No, those are radars that you can move, deploy it.
Okay.
Because the antenna is very small.
Okay, sir.
The transmit power, it's very light.
Okay.
So that's what makes it hard. It's like if it gets too bulky, because these are all deployable. They will just fit on a container and you can just move it very easily. Okay. And those are the, I mean, where is Subrata? You have to go see one of the X-band radars they have deployed.
I've seen that.
It's very small.
Yeah, it is small, but it like
and it
still
will, you can carry it on your car. Seriously, I'm not joking.
Sir. Not really, sir. I have seen that radar, so, but
the thing
it's more smaller.
FMCW is how you process this. It's more of a signal processing technology.
Right, sir.
The main thing is the antenna size and then the beam width. So it's R theta. Okay, so the radial resolution you can always maintain to 100 meters. The cross resolution is R theta. So if you make the antenna small, the theta will become big. Let's say you have 2 degree beam. Okay, say you limit the radar to 10 kilometers. You can compute your R theta. That's what determines your resolution. So it's not FMCW versus pulse.
Okay.
FMCW versus pulse is because of you might have been, that's the problem. A lot of people who do FMCW radar, they do low power radars.
Right.
Those low power radars cannot go to far distances.
More than 100 meters.
So you automatically think you need only FMCW radars to look at short ranges. That's not necessarily true.
Okay.
You can do pulse radars with solid state pulses and they can also be made short range. Because inside the pulse, the modulation in a solid state radar is a FMCW signal.
Okay, sir. Okay, sir. Thank you, sir.
Thank you.
Thank you so much, sir, for your insightful deliberations. With all the questions coming from the audience, I believe You have left a significant impression on their minds and ignited all the young minds sitting over there. With these few words, we will now proceed for the last but one session of today's program, which is the hands-on training on radiometer and radar profiling by Society for Applied Microwave Electronics, Engineering and Research. The session will be led by Head of Atmospheric Division of SAMIR, Mr. Ajay Khandare. I would like to request Hafiza Begum and Julie Hazarika to felicitate Mr. Khandare with a Fulam Gamusa. Welcome, sir. With these few words, I would request the team from SAMIR to take over the session. Over to you, sir.
This one, no? So how we have to do it?
Pointer, this one.
Achha, only pointer, no? Okay.
आपको slide changes है.
Not required, not required.
ये तो आपका slide changes है, तो आपका इससे भी कर सकते हैं, इससे भी कर सकते हैं.
That's okay.
और इससे भी कर सकते हैं.
ठीक. Yeah, good afternoon everybody. Myself Ajay Khandare. So today our topic is hands-on training on radiometer and radar profiling. So before I start my talk, I would like to thank our Director General, Mr. P.H. Rao, Dr. P.H. Rao, our Program Director, Rajesh Harsh, and iRAD organizers to give us the opportunity to deliver the talk on this topic. So today actually we'll be covering hands-on training. So right now the system is not there, but still we are calling this as a hands-on training. So we will be trying to give the virtual feel of the system, radiometer system, and also I will take an opportunity to give a atmospheric related activity what SAMIR is carrying out, and SAMIR's other activity also, which are actually SAMIR is carrying out from last 4 decades. So those who don't know SAMIR actually, let me tell you, SAMIR is a Society for Applied Microelectronics and Engineering and Research. It's an autonomous body under Ministry of Electronics and Information Technology. SAMIR has got 5 centers. So head office is at Mumbai, then Chennai, Kolkata, Guwahati, and Vizag. So SAMIR key area of research is strategic electronics. So SAMIR is mainly involved in NDT LINAC, which is the flagship program of SAMIR, which is being used by the ISRO for their satellite mission. Without this, no satellites can be, actually the satellite program cannot be successful. This is a high energy scanner basically, which scans the satellite, and after that only the satellite is flown. And SAMIR is also involved in DRDO programs, so like SAR, altimeters and all. So SAMIR is supporting DRDO for their strategic activities. Under societal application, SAMIR is involved in atmospheric instrumentation. From last 3.5 decades, we have developed several radars. Also, SAMIR is involved in medical activities. So SAMIR has developed radiation therapy machine, and recent actually medical development is MRI machine, which is the indigenous MRI machine. It is getting deployed at AIMS in next month. Then under next generation technology, SAMIR has developed 5G testbed, 6G, actually SAMIR is leading as a major in under Bharat Alliance, and also SAMIR has got a services facility like EMI and EMC. So under atmospheric instrumentation, SAMIR has got an experience. Last 3.5 decades, SAMIR has developed several radars, and it is established and it is deployed all over India. So SAMIR has got a close ties with IMD, NARL, SPL, IITM, NPCIL from last 3.5 decades. SAMIR has designed, fabricated, installed TRL 8 to 9 level atmospheric remote sensing radars in VHF, UHF, K-band, SODAR, radio sonde, and many more such systems. So Samir also has built an expertise in AI/ML based atmospheric based data processing. So last 3.5 decades, Samir has worked in all these 4 areas, basically radar based atmospheric instrumentation, under that MST radar, wind profiler, ST radar, radio acoustic sending system, cloud radar, and HF radar. These all radars are developed by Samir successfully, and they are deployed in various parts of India. And then radio sonde system, 401 megahertz radio theodolite system, all over India, more than 15 installations are there. Then radio sonde data auto computation system, software, hardware, that is also developed by Samir. 1680 megahertz, 403 megahertz GPS digital radio sonde system, that is also developed by Samir and deployed various parts of India. Then ozone and radiometer sonde, these systems are also developed by Samir and they are deployed. Then GPS pilot balloon system, that is also given to IMD. IMD is using it extensively. Under passive atmospheric remote sensing system, Samir has developed dual band micro radar, which is our topic for today's discussion. Then lightning detection network, ionospheric scintillation receiver, and handheld sun photometer. These systems are also developed and deployed at various places in India. Under IT-based atmospheric data processing solution, real-time estimation of precipitation water using GPS, all these IT products actually Samir has targeted and it is deployed. So I can say Samir is contributing towards the Atmanirbhar Bharat mission of the Government of India extensively. Truly I can say. So I will cover very basic, very few atmospheric remote sensing radar system because this is the radar conference. So we would like to give the details of 4 major radars what Samir has developed. In 1995, MST radar is developed by Samir, which is installed at Gadanki, and it is still functional. Now we know this as a NARL, so that facility is taken over by ISRO, and now that MST radar facility is converted into national facility basically. If you see 1996 to 2022, Samir has developed SODAR, phase array SODAR. They are deployed various places in India, more than 15 locations, and they are functional. Samir is providing support for that. Then wind profiler in 2001, 404.37 megahertz. Wind profiler is installed at Pune, and it was functional for more than 17 years. I think last 2-3 years back they have decommissioned that. ST radar today this ST radar is developed and it is installed at Guwahati. I think there will be the demonstration today. You will see what Samir has developed. Then cloud radar and XA band radar actually for urban forecasting. That is our next target. So this is MST radar. It is developed by Samir in 1995. It is deployed at Gadanki and it is still functional. It is giving the upper air data up to 25 kilometers. This is the next radar, 404 megahertz, 0.37 megahertz wind profiler, which is installed at IMD Pune. It was running for last 17 years, and it has also got the RAS attachment for the temperature profiling. We could get up to 3 kilometer temperature using RAS attachment. So phase array SODAR, it's a successful program of Samir. That is SODAR means actually sound detection and ranging. So more than 15 places actually we have installed. Our customers are NPCIL, ISRO, IITM, IMD and universities. So this is useful for the pollution modeling and studies, climatological studies, sea, land boundary layer studies, potential wind energy studies. So it is capable of giving the wind profiles from 30 meters to 300 meters at the resolution of 30 meters. It is very much useful in the upper boundary layer studies. So also Samir is providing the maintenance to NPCIL sites. So this is our TRL level 9 level activity. This is a very successful product from Samir, and we are still open. If anybody wants actually, we can definitely provide that system. So these are the installation all over India. So more than 15 places we have installed this system. This is also one of the major actually successful product from Samir. I can say this is the TRL 9 level product for ionospheric study. So Samir has developed ionosonde system, which is majorly used for the space weather studies. So this is deployed at Dibrugarh, then IIT Prayagraj, and next system we are going to get deployed at SPL ISRO in Bhopal. So this is giving us the actually real-time electron density profile and ionospheric drift. So this has got, you can see, this is the 21-meter height antenna, dual polarized antenna. It is installed and it is actually tested at site only. And this is the receiver and this is the ionogram what we are getting there. This is the ST radar. Organizers are going to take cover actually this demonstration, so I will not speak more on that. This is being developed by Samir fully and it is being installed at Samir Guwahati. And this is working at 212.5 megahertz. These are the actually some of the power spectra received from the 5 beam, which is giving the vertical wind velocities. So our today's topic is micro radiometer. So this topic actually we are trying to give you the feel of the virtual radiometer hands-on training. So this will be covered by myself. I will be covering the hardware and some of the actually major part of the system. Then my colleague Mrs. Diveshi Shinde will cover the operational part of that, and Mr. Abhishek Jha will cover the data products related topic. So if you see, this is the micro radiometer which is installed in Northeast India region for climate modeling and weather changes. This equipment is possible, is capable of giving 24/7 temperature and humidity profiles. So why microwave radiometer is required? So currently if you see there are two methods, radio sonde and satellite. So radio sonde is a weather balloon. As we know, twice a day actually IMD flows the hydrogen balloon with the sensor and we get the vertical profile of the winds. But it has got certain issues basically. If you see, it can go up to 20 to 30 kilometers, that is the advantage basically. But if you see the limitations point of view, sounding is available only twice a day, then lateral drift is there, elapsed time, this kind of issues are there. Then there is a second method actually, satellite based geostationary and lower Earth orbit method to study this temperature and humidity profile. But there are also actually limitations, basically large footprints, less accurate in lower atmosphere, then revisit time is more. So to get the solution, radiometer is the ultimate product which can give you the vertical profile of wind, temperature and humidity at a very good time resolution and very good height resolution also. So Samir proudly says that Samir has developed indigenous radiometer and it is deployed at IMD, and we are likely to get 17 numbers of order from IMD for the same system. So this is the specification for micro radiometer. This is mainly operational in K band, which is catering the temperature, and V band, which is catering the K band, it is catering the humidity, and V band, it is catering the temperature. It has got the frequency agile channels, so 12 to 15 calibrated channels are there. V band actually 51 to 60 megahertz it is working. It has got more than 8 calibrated channel. We are targeting here liquid water 22 gigahertz to 31.5 gigahertz. Brightness temperature 5 to 400 Kelvin, and maximum height we are targeting here is a 10 kilometer. So vertical height resolution we are getting here 50 to 250 meters, from 100 to 2 kilometer, and above 2 kilometer it is 400 meter to 1 kilometer. Indication time is 1 to 10 seconds, and humidity range we are getting 1 to 100% actually. Accuracy plus minus 3%. Then accuracy resolution 0.1, 0.5% and 0.1 degree. That kind of accuracy we are giving. This has got both the scanning method, azimuthal and elevation. It is scanning, and we are trying to get the data of the temperature and humidity. This is the typical micro radiometer block diagram. You can see we have got the flat plate reflector to receive the atmospheric radiance available in K and V band, and this is being captured by K and V band antenna. It is being amplified by K band and V band receiver, and then that voltage is detected by voltage is digitized by our radiometer data acquisition system, and we are passing this voltage data to convert it to brightness temperature. That brightness temperature, we have developed the retrieval algorithm for computing the temperature and humidity. That will be covered by Abhishek Jha, and then we are trying to get the real-time profiles for the temperature and humidity. This is the same actually is the block diagram what I explained now. So these are the actually components indigenously developed by Samir. That is a dual band antenna, K-band agile receiver, V-band agile receiver, then local oscillator, data acquisition unit for the digitization and processing, and flat plate reflector. So you can see here, this is the total integrated system inside. Basically, this is being installed at IMD RMC Guwahati. So this has got also azimuthal control, 0 to 360 degree. We can go and we can receive the data. So rest of the part actually my colleague Divesh will take care. So we have got a stall here actually. We are displaying all the products of Samir. You all are welcome to visit our stall, scan the QR code, and you will get more products what Samir has developed. And any questions are there actually after her presentation and Abhishek presentation we can take up. Thank you.
Thank you, sir. Good afternoon, everyone. This is Diveshri Shinde. I look after radiometer hardware design and development. My major contributions are the entire embedded system development, then the GUI development, followed by the overall system integration, and then the deployment of the system at RMC Guwahati. So today I'll walk you through the entire operation flow of our system, which will eventually give you the look and feel of our K and V band radiometer system. But before I proceed, I humbly wish to show you something. Recently, during our TechVerse event, we had the launch of our system in the honorary presence of Mighty Secretary and DGIMD, Dr. Mrityunjay Mohapatra ji. So let's have a look at the video, which will briefly describe our system.
Samir proudly launches its indigenously developed atmospheric radiometer system, a cutting-edge ultra-sensitive passive receiver for atmospheric profiling. It operates in the K band, that is 22 to 30 GHz, and V band, 50 to 60 GHz, to detect radiation from water vapor and oxygen, generating accurate temperature and humidity profiles up to 10 kilometers. The system offers full sky coverage, real-time scanning, and 24/7 atmospheric data with high resolution. Now active at IMD Gauhati, it supports continuous atmospheric monitoring.
Thank you. So from data acquisition point of view, I'll highlight major features of our system. It has user-friendly GUI for seamless instrument control. It is designed for robust and reliable 24/7 unattended operation. It has Python-based GUI, which is controlled by an embedded system, which is controller-based. So commercially available radiometer systems normally have processor as their controlling unit, which normally takes more power. So our design, which is completely in-house and a custom design, it takes less power and it is simpler compared to those. Then this system also supports, as sir already mentioned, azimuth as well as elevation scanning. I'll talk about it later. Along with normal sky observation, we have also integrated surface sensors to enable surface data accumulation. And this entire data acquisition is completely automated along with real-time as well as offline results visualization in terms of plot as well as CSV. So this is the entire block diagram or entire view of our system. The radiometer system looks like this. This is installed at RMC Guwahati. These are the internal subsystems of the radiometer system, which is explained by Khandare sir. Now, the front end of the system is dual band receiver. It has K-band receiver, which has 8 channels. Then it has V-band receiver, which has 14 frequency channels, so total of 22 channels we have, and all the frequencies are set up by this LO synthesizer. So this is a cutting edge millimeter wave based technology that we have tried to done in-house at Samir. Then the voltage, so it will get data from sky and convert it to voltage values. So these voltage values are refined and signal conditioned in our RDAC system, which is radiometer data acquisition and control system. Along with it, it will do the surface sensor data acquisition, and it is like a heart of the system. It will cater to all other processes to run the instrument. And these final voltage values are passed to UI, and which finally converts it to vertical profiles of temperature and humidity and brightness temperature, which you are interested in looking at. So now to understand the operation flow for our instrument, we have to understand how to operate its GUI. So it's very simple. We just have to set up the observation file, which is a configuration file. Then we simply have to click on the run button, which is execute button, and you will get your plot data. All the customizations are possible. What kind of plot you want to see, what kind of observation parameters you want to set up, all those customizations are possible. So apart from this, as I mentioned, RDAC is like heart of the system. So if anything goes wrong with that, we should be alarmed and indicated immediately. So we have a separate module to view its status and control instructions. Then diagnostics module is also there for troubleshooting and testing purposes. Then we, to carry out the LN2 calibration of the system, we have designed a separate module to automate the entire calibration process workflow. And then there is help. So this is how the GUI would look like when you open it, and it has all these options to help you navigate through it. So our basic aim is to go for system observation, sky observation. So in this, the major modules are sky observation, calibration, frequency channels, and data analysis. So as I mentioned, for your experiments, you would want to play with different system parameters. You would want to change that. So we have given that provision to customize any parameter of your interest. So I'll talk about sky observation later. In calibration, this is talking about auto calibration. So how many times you wish to see the black body, at what repetition rate, all of that information you can set up in this. Then in frequency channel, as we mentioned, in K-band we have 8 frequency channels, and in V-band we have 14 frequency channels. So total of 22 frequency channels. So in that also you can customize and select whichever channels you are interested in. And finally in data analysis, whichever data plot you wish to see, you can select that, and that will be plotted as a result of our observation. So under sky observation, sir briefly mentioned about azimuth and elevation scanning. So under elevation scanning, we have 3 major options, which is fixed angle scan. You can set fixed elevation angle, and every time system will automate that flow and take that fixed elevation angle. We also have the provision for bilateral scan, wherein you can decide number of bilateral scans you want. And finally, we have a fully customized user-defined scan option, wherein you can put whatever elevation angles you want and system will work accordingly. In azimuth scan, we have the similar fixed angle method and also the anti-solar tracking method. So currently we are using this anti-solar tracking method. So in this, at all the time, based on the GPS data that we receive, our system will face opposite to sun, so that we have a better signal reception quality. And also the integration period is customizable. It starts from 400 milliseconds and can go up to 10 seconds. As we all know, the integration period affects sensitivity of the system big time. So higher the integration period you set, better the sensitivity you are likely to receive. Similarly, we can customize observation start time, or if we want to start it immediately, that option is also there, and termination as well. We can predefine the number of cycles that we wish to execute, or we can have unlimited mode, which is like a completely unattended mode. You don't have to sit near the system. System will function on its own, and you just have to go and see the result whenever you are interested to see the result. So this was all about the sky data collection. Now after that, we produce results of that data. So these results are in two major formats. One is CSV, and other one is the actual visual plot format for the results. As I mentioned, we have a lot of surface sensors like pressure, temperature, humidity, rainfall. So all that surface data will be available under environmental data plots in plot as well as CSV format. Then for sky data observation, we are plotting all the received voltages values with nicedoid on and off, and also all the brightness temperature values. So those can be observed under sky data observation plot as well as CSV. And after that, finally, the product of your interest, the process data. So for that also, we have CSV and plot visualization. We have vertical profiles of temperature, humidity, time series plots, and skew-T plots. So all of this data acquisition flow is completely automated, and you will have a status module like this, which will show you the current cycle which is going on, and if anything goes wrong with the system, if any flaw occurs, you will be immediately highlighted over here. And all the received data is systematically stored in L0, L1, L2, and L3 data folders. L0 is raw data, L1 is process data, L2 will have brightness temperature related values, and finally L3 will have profile values. So this was like an automated flow for the system. But you all are scientists, you might want to handle system manually. So we have given that provision as well. So in this, all the parameters you can customize according to your choice, and like a single stepping approach, you can see the result of your parameter selection and sky data related to that. Now for calibration control, we have automated the LN2 calibration process completely over here. This module can perform multiple cycles of LN2 calibration along with its verification. So post calibration, you will generate system noise, system temperature data. Once you agree with the value produced by the instrument after LN2 calibration, then you can log that value, and finally those calibrated values of system noise and noise figure will be used for the further brightness temperature measurements. So user has given, we have given that right to the user to finally say yes or no to the calibrated value. So yeah, that's all from my side. Now, I know this is all about the hardware design and its development related activity for radiometer. I understand we do have a lot of scope for improvement, and we look forward to your valuable suggestions. And now I'll hand over to Abhishek Jha, who will talk about applications of the radiometer and then the further topics.
I'll do it. Thank you, Devashree. And good afternoon, everyone. I am Abhishek Jha. I work as a scientist B in Samir, Bombay. So I look after microwave radiometer data algorithms, calibrations, and science, basically science parts and validation of the physical parameters derived from the instruments. So this is just for an overview. These are the milestones in the field of atmospheric science related to observations. Right from the 1922, we have come along in different technologies, both active and passive sensors that can be used for deriving multiple geophysical products. So this, if you see, this is the electromagnetic wave spectrum outlined for the use of different frequency band to probe into the atmosphere to derive atmospheric parameters, and those are based on the principles of absorption, emission, transmission, reflection, refraction, and scattering of the target molecules as well as particles in the atmosphere. In the previous talk, you were listening that Professor Chandra was telling about the scattering cross-section. So those comes in the active remote sensing. And here I am going to talk about the passive remote sensor, which is microwave radiometer. Basically, these measurements are used to form some scientific understanding. Observations can lead to scientific understanding, hypothesis, to build hypothesis, and that can further used. No observation, no instrument or test bed is developed only to monitor the system. So because if you are from meteorological background, so you know we have two terms in the numerical weather prediction models, diagnostic as well as prognostic. So in diagnostic, we can get the information, we can see, we can track with these observational instruments and systems by the synergy of different sensors. We can track the system in real time, spatially, different location, we can have the observations, but we cannot have the future integration, we cannot have the prognostic variable, that time dependency, we cannot get the future measurement from these observations. So adequate understanding of the physical processes are mandatory owing to any instrument, so that we can build some mathematical model that can be further used, and we can shift our test bed to some other places to better understanding. So these are the way we form, generally it is formed for this observation test bed in atmospheric science. So how to connect these observations into for a reliable weather prediction models and forecasting. Here you saw this is observation domain and this is forecasting domain. So observation domain, we can have different sensors from the ground-based instrument to space-borne satellites, sensors in the satellites. So these sensors, you get, either you send pulse electromagnetic waves and then you derive quantities from based on the reflection, refraction or scattering, which is active. Another thing, these gaseous pollutants or molecules in the atmosphere or any particles, they have, based on the Kirchhoff's law, they can absorb and they can emit, even though it is not perfect black body, some sort of radiation it can emit. So we can design our sensor to capture those emissions. So, but those emissions again you will get in the form of power, maybe, or some electronic parameter, equivalent parameter, maybe voltages, or maybe if it is emitting, then you can measure emittance, that is, or radiance. But you need to convert these parameters into your quantity of interest here. So these signals in the voltage form, that is converted into the observation domain parameters using reliable retrieval techniques, and those are further will be used in both in understanding the physical process and to form some mathematical model, or as an initial and boundary condition to give the existing numerical weather prediction models such as WRF, WOP, and other models. So that it can predict reliably. So if you give correct information, initial and boundary conditions with a better observations, you will have a better forecast with a greater lead time. So in atmosphere, any system, it will start from raw and dry air dynamics. So these dry air further captures moisture, whether it is transported from, whether it is advected or it is locally generated, coming from the vertical flux form or maybe from some remote agency. So these, then it will start, condensation will start, then cloud will form, and then multiple cells of cloud will accumulate, it will form a system, and then it will rain out. So to forecast and to make some physical model or mathematical model, we must have information and or observation to entire span of the system. So these are the several sensors that can be used to probe the atmosphere, and we'll get these parameters. This dry air and humidity we can get from the dual band microwave radiometer, which I will be talking about today. Others are radars, millimeter wavelength radars and centimeter wavelength radars you heard in the previous talk by Professor Chandra. So these radiometers are basically passive. It doesn't send any signal in the atmosphere. It is like an ear. It will be listening to the emitted signal in the atmosphere by the atmospheric constituents. So our goal here is to measure temperature and humidity profiles continuously. So now to measure these temperature and humidity, this is based on the absorption or emission spectra of the molecules. So those concerned molecules are, for temperature we need to have water vapor absorption, and for oxygen, for temperature we need to have oxygen spectra, and for water vapor we need to have this water vapor channels, like for humidity measurement. So to devise this instrument, whether these are like what channels we need to choose and what is the bandwidth, that can be done some prior simulation or maybe some spectroscopic analysis in laboratory. So this is one simulation we did based on the actual data over the Guwahati region from radio sonde data. I have used here Libe model. This is absorption spectra model. And you can see here that 20 to 30 gigahertz we have a peak in water vapor channel, and 50 to 60 gigahertz we have a peak for temperature channels, which is oxygen spectra. And we have, just in the previous talk, Devishri was explaining, we have 22 channels in different, in these two bands. So those channel has been chosen based on the resonance frequency. Basically, these are absorption models. If you look into the model, this is based on the rotational spectra of the rotational dipole moment of these two molecules. These molecules emit, but they have their own degree of freedom. So if you derive the equations of those, like this spectrum, based on the quantum mechanical theory, you will find some resonance frequency. Those resonance frequency have been chosen for central frequency, and based on the pressure broadening, which is Doppler, in the shift in the frequency, we have kept bandwidth. Now, the point here is, why do we need to have another observation? We all know weather balloon we are giving. By far, weather balloon is the best measurement for temperature and humidity in terms of accuracy. You will have measurement every 10 or maybe if you do quality control, maybe up to 50 meters resolution we will be getting the data, and up to 30 kilometers we will be getting. Still, why do we need to have some alternative measurement technique for getting measurement from atmospheric profiling? So I'll try to give you an answer in two ways. The first is, these balloons are like physical entity. So those sensors are kept inside the balloon, and then it is being released. So with the wind, based on gravity and its own mass, it will go up. And if there is a background wind, it can be advected to some other place. So it drifts, basically. So based on the GPS sensor, if you can track easily where it started and where it went in at what vertical levels. So based on this, you can see at 10 kilometers, it drifts more than 50 kilometers. So if you are targeting your measurement here, at 10 kilometers, you have a temperature value that is basically not looking overhead, and you are measuring somewhere else. So now, based on this coordinate system, you can see it started here, it drifted to here. So now, if you want to check how reliable it is, the point comes that background atmosphere doesn't change much. At 10 kilometers, you know, temperature profile is not going to change much. But mean state will not change. So if you simply see here, it started here, it went to here. If you calculate dt by dz, dt by dt of smaller t, the t is temperature, or any variable you can take. Moisture you can also take. So at this point, this is t prime, I kept another variable that this location, how it is changed over the time. So based on the total derivative concept, if you see, local derivative is dou by dt, dou t. So this can be different at two places. For instance, you just assume that over locally it is not changing. But these can change much. So this zonal and meridional component, which is like convergence due to the background winds. So it is quite possible this zonal or meridional wind can have like jet kind of thing, and you will have similar convergence. But when you have some perturbation from the background state, and then some systems is developing, and vertical velocity can go up, can change to that particular location. And the last term, the vertical transport term, will be much different than the background mean state. So that can lead to huge change in the dt by dt over time. So we need, there is a possibility, this is in terms of temperature. If you try to see in terms of moisture, so vertical transfer of moisture, if some system will be developing, it will transport the moisture into the upper atmosphere. But since your balloon is not there, it is somewhere 50 kilometers east or west, somewhere else, so you will not capture those moisture transport. So there must be some fixed platform measurement should be there. The second reason, balloon, you have only twice a measurement. So morning, evening, you are launching and you are having. But atmosphere have a diurnal evolution. And even if you can force and model your diurnal cycle for mean state, but when some system develop, you don't know actually before that what was the background dynamics, what was the temperature and humidity profile before some storms or maybe some systems. So here you can see, in this work we tried to see the diurnal cycle of convective storms. These are storms, frequency of storms within a day, and composited for 9 to 12 years measurement, I guess, based on the TRMM satellite. And this is ground-based radar, S-band radar. Here you see it starts over the oceanic region, and then within a day, how it evolve and go over the land region. Even you can see these within 0 and 12 VTC, you have sufficient number of storms. And those storms are deeper. It can go up to 8 to 10 kilometers. So when these radio sounded data of morning and afternoon being assimilated into the numerical weather prediction model, so that to incorporate the physics of atmosphere in terms of convection or radiation, because this change in the temperature or humidity can lead to radiative cooling, so the formation of clouds that can further lead to radiative cooling or radiative heating. So in this fashion, generally it is being incorporated, traditional convective or radiative parameterization schemes. So here, the first thing, if this grid, you have measurement giving radio sound at 10 kilometer, you will have this grid value. so physics will not work. Your forecast is likely to be going to be biased. And another part, that these convection itself within 0 to 12 UTC, you don't have any observation. So you are not making your model to parameterize those measurement within continuous a day. So we need to have an observation, around the clock observation. Every hour we need to incorporate into the models. For that, the solution, like it is the microwave radiometer. In the previous talks, it has been covered. This is the overall subsystems to data products. I'll be going to talking about how these data products are getting derived, and what is the accuracy, how good we are deriving these products, and validation. This is the overall process flow of the processing unit. We basically getting observation from radiometer in the electrical form, that we are doing some calibrations against the black body. We are looking into the sky, getting the radiance from the sky. We're converting into the voltage form. And then next cycle, we are looking into the black body. Since black body, you know, from Planck's law and all the radiative transfer theory, if you can recall, for a black body, brightness temperature and temperature both are same. So there should be some reference for a calibration. That's why we are using black body here. So this black body, it is at the place of radome. Like here we have kept inside. This is a receiver, and here black body is kept. Once a reflector is there, it will look to the sky, get measurement, then then another alternative, it will look to the black body. So by that, then solving some set of equations, we are getting actually the calibration coefficients, and that we will be using the real-time measurement for deriving the brightness temperature. Those brightness temperature, again, it is a column average value, which is equivalent to some radiance emitted in the atmosphere, but not actual physical temperature value. So to derive it, we need to have some technique. That is basically inversion technique, as that I will be going to speak in the, going to discuss in the next slides, why it is inversion and why it is so much problematic, so that we need to construct some good and accurate inverse model. These are the data products, like this temperature and humidity profiling, and these are the derived product we are deriving from this raw equivalent potential temperature, and then virtual potential temperature. This is like thermodynamic diagram we are generating from these products in the real time also. This is raw level 0 product in the electrical form. This is receiver detector voltage. At K band I have shown here. Similarly we have in V band also. These are like frequency probability distribution at different frequencies. And then we can try to see whether it is capturing the actual compared with the other system as well, and it comes in reasonably well within the limit. Now to convert these electrical parameters into some physical products, which is black body equivalent temperature, we call it brightness temperature. So for that we are doing some self calibration. Basically we are injecting noise. See, the emittance by these molecules are, if you look in terms of signal, these are very, very weak signal. About more, like minus 110 dBm, the value of signal will be there. So it is very hard to capture. And also, there is no reference. So the best way to capture is how much difference it is reflecting. So noise diode is kept inside. So once measurement we are doing, it will look to the sky with noise injection, and then other time without noise injection. So we'll get the difference. And similarly for the black body, and then we'll be solving those equations using in the real time these, and then those like TV will be in terms of those parameters, but it will have some like non-linearity. It has some non-linearity. So those are based on these calibration coefficient. I'll be talking in the next slide. We are doing some absolute calibration. We're putting some liquid nitrogen overhead and then trying to get the radiance from the coldest and hottest load. So under this, basically, when you are getting measurement from the atmosphere profiling, let's see up to 10 kilometer, from ground to 10 kilometer. So at surface, you may have some few 30, up to maybe Guwahati. We have developed these and like deployed this system at Guwahati. So maybe in the range of 30 to 40 degrees Celsius, maybe 40, 45, up to 40 degrees Celsius, you can assume whatever value you can think of, and physical values. And then up to, at 10 kilometer, if you see the standard atmospheric temperature profile, it goes up maybe minus 70 or minus 65 degrees Celsius, up or in that range, in different season. So to solve this and to get, during calibration, what you do, so whatever measurement you are trying to do, you try to replicate it in terms of some reference value. So we should have this radiance coming from some object which is black body itself, and also it is like attaining the temperature of minus 60 degrees Celsius. For that, we are dipping our black body into the liquid nitrogen, and one black body we are keeping inside for the hot load and hot and cold load, so that the lowest level of atmosphere, highest level of atmosphere, you can get radiance from. And then since this is black body, so there will be direct relation, and then solving these 4 equations. If you see these 4 equations, like these are algebraic equation, and every term is a term like substitution, and you have to substitute and recalculate. So you have to start with some initial guess, and then you can reiterate it and look for the convergence of the solution, and then you can get those parameters. So we did it. We did some cycle of calibration, and we calculated all those parameters. Just for example, you can see when you put this liquid nitrogen into the flask, it is compressed. But when you kept it outside, then you see with temperature, ambient temperature, it will automatically, pressure will be started dropping, and its own temperature will get changed. So we need to keep track in that. For that, we try to model those liquid nitrogen boil, which is like cryogenic temperature. So to map it in terms of other sensors which is deployed over the site. So for that, we tried some other radiometric and RPG systems. They are using these predefined equations. They have done some experiment. So we also did, and we found that our TC temperature of the cold target comes in the form of this. So even though we are knowing, when you are buying the liquid nitrogen, you know at what temperature it will be. But with time, when you put it into the flask, it will change. So how much change it is there. If you do not have any sensor inside, you need to model it. So we did it. Then our observation as well as like theoretical models using Clausius-Clapeyron equation, it comes within the range. And these are like just to check the consistency of the loads, hot and cold loads. Further, the one question arises here. We are trying to get the radiance from the black body. So the first thing we need to make sure that the radiance coming from the cold load, it must attain the temperature of liquid nitrogen, because it is a black body. Just like a hot load, when you are putting into the liquid nitrogen, it should come into equilibrium with the liquid nitrogen temperature. So we just using the material composition of those, an area of the black body, and then using the thermal capacity and this rate of loss, it will be in the terms of rate of gain, and then you solve, you will get this time bond. So lower bond is 3 and 23 minutes. So at the worst condition, even if you consider the material is worst And then also it will, within 20 minutes, it will reach to the equilibrium. But then challenge is, then you will have less number of observation, because this gets evaporated very quickly. Within 30 to 40 minutes, it will get evaporated. So we need to be cautious. And now after getting brightness temperature from this calibration, now we need to convert it into the physical temperature profile and humidity. So for that, we need to have some law. For getting any parameter, you need to have some law. If you have some physical law, for example, Ohm's law, you know F is equal to ma. If you are measuring somehow A, you can get m, right? But the problem here is there is no some universal law for getting temperature and humidity profile directly from the brightness temperature. Why? I'll let you see. If you recall the laws of radiative transfer theory, these black body brightness temperature, if you remember, B nu is equal to something, and then e ki power h nu by kT minus 1, if you remember in your bachelor's, Planck's law, Planck's curve, and if you convert it into the, that is basically flux. If you flux equivalent temperature, that is actually the brightness temperature. So this comes in this form. This is the terrestrial temperature, which is cosmic background temperature, which is a fixed value, and this will be the brightness temperature. Where this is temperature data, this is weight. This weight function actually we need to get from the observation of temperature and humidity data. So now if you calculate this, if you have temperature, you can directly calculate TDA. But if you have this brightness temperature and you want to get temperature, then you have to invert this. But this type of integral is not like, it is called freehold, some name I am forgetting, integral, which is like, that will not satisfy the criteria of a unique solution. So a multiple value, different types of brightness temperature, a set of different types of temperature profiles can lead to the similar brightness temperature. Therefore, it is ill-posed problem. So we need to look into some other alternative way. So other alternative way is, if you do not have observation, then you can use this to simulate some brightness temperature large data set, and with this temperature and humidity profile, you are getting this set of brightness temperature at different frequency, and you can collect a large amount of data, and then you try to map into inverse way, and you get some inverse model. Or maybe simplest way I can tell you, you can get some regression coefficients. So for that, you need to have for simulated brightness temperature prior to your observation. Since you are going to develop your instrument, you will not have instrument data, right? So you have to rely on to the like simulated parameters. And also, to construct any algorithm, you need to get assure that instruments inherent bias should not come. So it is advisable to use some model synthetic data to construct algorithm, and then instrument automatically will respond to any further perturbations. So for that, we have used RTOB, this is a community atmospheric radiative transfer model, and then we have used prepared input data set for long term both from radio sonde as well as reanalysis products like ERA5, MERA2, and IGRA product, which is also radio sonde but quality control radio sonde. I'll show you here. So these are the data we have prepared for the simulations. Here you see this is from the radio sonde, which is very high resolution, up to 50 meter up to 1 kilometer, then about 100 meter above that, 2 kilometers. And this is from reanalysis coarser resolution. But the idea to get this, even though this is not the true observations, this is numerical weather prediction models output with the data assimilation technique. But you don't have complete diurnal cycle data. So in future, if you want to make your system sensitive to the entire diurnal cycle, then your model need to learn those data set as well, right? So for that, we have kept this ERA 5 and MERA 2 data as well. These are the surface parameters. It's 2 meter surface temperature and 2 meter surface temperature and then pressure. And these are the hydrometeor contents. One more thing, this is completely absorption model. So there is no scattering given into the model. So whenever there will be rain, so the scattering from the scattering of these in the range of those microwave frequency will not be able to capture into the instrument. So during rainy condition, model may or may not be perfectly working. But cloudy condition, we try to aware our model using these hydrometeor profiles based on the large, longer time data taking from the ERA 5. At least it will capture the trend. I know this is not the true data, not getting from any instrument, but this is like at least will give a monthly trend. Based on those two type of data, we have simulated brightness temperature. You see, then from radio sound high resolution, it will it's like in K band you have little higher value it is reaching up to in terms compared to the reanalysis simulated data. Because this is sensitive to moisture profiling. So you know, ERA 5 or MERA 2, any reanalysis product is underestimating the moisture content or moisture profile. Based on those simulated data, we tried to construct one model, statistical model, but multiple statistical technique we adopted. We invoked the AI, ML, machine learning algorithms as well. We tried to use some physical model as well, other than this statistical model, which I'll show you in the next slide, which is optimal estimation method. So from here, these all 4 or 5 types of machine learning model we tried to invoke, we tried to train based on the 80% data of brightness, temperature, and concurrent temperature and humidity profiles. And these are the model's performance. These are evaluation matrices for humidity. You see, well within 2 gram per kilogram in the lower atmosphere. Just 5 minutes, I will go. So, and for temperature, you see, like lower atmosphere, it is well within the 1 Kelvin, but it goes higher up to 2 or more than 2 in the 8 to 10 kilometers. Again, this is single using radio sonde, but when we combined both the reanalysis and radio sonde, it slightly changed, and we have better accuracy. But these are like on the test data, so we need to validate these models when we integrate it with the real-time system. After integrated with the real-time system, over the site, we compared the observation with the radio sounded ascent, and you see these are the root mean square error, which is well within the limit. If you compare the accuracy of other existing system over the Indian sites, these are the other systems working over the Indian region. Again, the RMSE for both temperature and humidity profiles are like was in our case. So the point here is, with any system, you can expect up to the 3 or 4 Kelvin in the higher levels, and up to 2 Kelvin, 1 to 2 Kelvin in the lower atmosphere. Just finishing up. So these are the potential sources of error. Positional error, which is due to the radio sounded drift. Other ones are inherent bias in the MWR measurement itself. Another ones are while we are converting voltage into the brightness temperature. And the last one is due to the inverse model. This using numerical weather prediction model, and they try to mimic the radio sonde launches in the numerical model, and they quantified. It could be up to 3 degrees Celsius RMSE. So anything up to 3 Kelvin can be considered due to positional growth, positional error. So radio sonde itself is not correct, because it is correct, but it is not over that location. So one-to-one comparison is not likely to do. Next is due to the presence of non-met target, which could be due to the emissions from the different sources, and we try to mitigate that using standard deviation of the brightness temperature in a 2 minutes sliding window. And another thing was like this, since this model was not aware of the rain process, scattering process, so it is advisable when it is raining heavily, measurements are not to be used. You may get error very much fluctuating. So we have a rain sensor there. So while comparison, while doing validation, you can just filter it out based on the rain flag. And additionally, this lapse rate, historically we have computed. You check your radiometer data with the, you calculate the environmental lapse rate, and then see if it comes within the range, then it is advisable to validate for other things. Other than that, we are also use some optical estimation model, which is physical model, but this is like still we are doing, not yet completed. Some sort of result we try to do, but yeah, this is not coming, even it is not coming at par with the statistical model. So there is something wrong. We need to take care of that. So for that, we tried to see this. Two things are there: whether your measurement is accurately matching the best agreement, or whether it is stable solution. So we need to have some optimized value. So for that, we need to select some prior selection, like different seasonal prior can be used. Measurements, covariance matrix we have incorporated, but forward operator, the forward model we are using, we need to check whether how accurate it is. These are the future plans. We have derived some stability indices as well, and then further we will look after to develop some nowcasting kind of thing based on these radiometer data, combining with some other surface sensors like radiation sensor or maybe some other parameters. Other sensors can also integrate with this system, and you can derive the cloud-based height using iRAD radiation. And yeah. So thank you everyone for listening. Any question I would like to take up? No? Already late? Yes, yes, sure. Yes, yes, yeah. Thank you everyone.
Thank you so much, sir, for your informative session. So here we come towards the end of today's program, and from now, I request all the participants to proceed towards the ST Radar Center for practical demonstration. And before proceeding and making their way to the center, you can collect your certificates for today's program from the registration desk. Thank you so much.
Hello everyone, just an announcement that ST Radar Center is not so far. It's just 5-minute walking distance from here. We'll all go by walking. So our all volunteers, including me, will lead you to the center. Actually, there is a talk demonstration here, but since time is less, so I will not going to give any talk here. We'll do all the demonstration through that interaction session only in the ST Radar Center. It's just 5-minute way from here. So tea will be served there. We will having lots of interaction session, and that your certificate is ready. You can collect from the registration desk before leaving to the ST Radar Center.